Hey guys, as an advocate of GraphQL, I wanted to make sure the technology was accessible for everyone. So today I'm dropping a complete 4-hour course for free. In this course, we'll cover absolutely everything you need to know to go from zero to building production grade GraphQL applications. If you've never used GraphQL before, then we're going to start with the absolute basics, teaching you how to run basic queries and mutations before finally moving on to more advanced topics. The course is split into 2 parts, all available in this video. We have GraphQL Fundamentals and then GraphQL Mastery. So check out the timestamps below and you can jump to any section that you need. And if you do want to code along, there's a link to a GitHub repo down in the description. In this course, we'll also be building out a full GraphQL application. So grab the link and code along with me. And as I mentioned, this is a really long one, so don't expect to finish it all in one go. So please subscribe to the channel, save the video and jump back as and when you need. I hope you enjoy it. Let's dive in. In GraphQL, we can send a query with the query keyword. So we type query and then we use curly brackets to define the type of query we want to send. So in our case, we have a server that has posts, comments, and authors. I've already defined 2 queries on the back end. So let's call our first one get posts. We then use curly brackets again to select the fields we want to return. So in our case, we'll have ID. I think we can get the title there as well. Let's send that. And you'll see we'll get JSON back, which is the exact same shape as the query being sent. So you can see the query syntax kind of looks like JSON, except it's just the keys, not the values. But the shape of the data being sent back always matches. We can also request related data with this query. So in our case, we can grab the author of each post. So again, following the same syntax, I'll say we'll get the author ID and the name as well, and then resend that. And you can see for each post, we're also now grabbing the author. We could also get more related data. So I could say, let's get the comments of each post. I'll get the ID of each comment and the content as well. And let's send that again. And you can see now we have the posts, the author, and all of the comments. You'll notice that the comments are coming back as an array, even though we didn't define an array here. Because GraphQL is strongly typed, it already knows that the data coming back for comments is going to be an array. So we don't have to define any sort of array syntax. Let's look at a second query called getPost so we can pass arguments to our server. So let's change the query to getPost. Request some data. We want ID and we want the title of the post. But we still have an error here because it expects an argument to be passed of type ID. We can see from our list of posts, the first post has an ID of 1. So we can pass arguments using rounded brackets. I type in ID, colon, and then as a string, the ID. If I run this, I get only the post I requested. So this is a version of a query with arguments being passed. Now, nothing magic is actually happening here. It's just a network request. So if we look at the network inspector and then run this query again, you can see that all we're doing is sending a request to the GraphQL endpoint. That request is a post type, and the reason it's a post is so that we can send a body payload. You can't do that with get. The payload is an object with the query key, and the query value is the syntax that you see on the left. When the server receives this, it will know exactly what to do with it. It will compute what fields need to be returned and then return to us some JSON. Running mutations is very similar to running a query, just like we did before. So here we have the setup for our query, but we're using the query keyword. And for mutations, we just use the mutation keyword. In GraphQL, queries are for fetching data and mutations are for changing or updating data. So we've already got a mutation set up on the backend called createPost. We'll call that and we'll want to return the post ID and title. And we need to pass some arguments as well. So we use the same syntax as we did for queries as well. We say title, let's call it my new post. And then we need to give a user ID as well to connect it to a user. In this case, let's just use the first user. So you can see right now we just have 2 posts. And then if I run the mutation, we get the new post come back. And then when I request post again, we can see that our new post is here. Now, you can actually name these queries as well. So you can do the same for query and you can do the same for mutation. So in this case, let's call it createPost with capitals. And the reason we do this is so we don't have to pass variables inline. So in our case, let's say The title should be a string. The user ID should also be a string. And now we can pass these directly in. We also have errors here because the types don't match. So it says the variable title of type string using position is expecting string required. So we have string as optional at the moment. So I just need to put a exclamation mark there, and the same for user ID. In fact, user ID needs to be a type ID. So let's do that. ID exclamation mark. And now the way we would pass data is we have this variable section down the bottom here. So here we define a JSON object. We say title and we give it a string as well. My other new post, and then for user ID we'll just use number 1 again. So there we have it. Another post has been created, but we'll pass in a variables object this time. If we look at get posts, we can see our new post is there. Now let's just look at the network request again to see what was being sent. So I'll run this one more time. You can see a request is being sent to the GraphQL endpoint. It's still just a post request, but the payload this time is the query itself, so our mutation, and then the key variables, which has the variables that we've defined on the left as well. Both of these are passed up to the server. The server figures out what to do with that information and then creates the post for us. In the next video, we'll look at the server side, resolvers and implementation, so you can actually understand what's happening on that side as well. So when this interface, GraphQL loads, it sends a request to the server to say, give me the schema so I can work out all of this IntelliSense up front. If we click on the Document Explorer, we can see our schema is defined here. So we have types for user, post, comment, and then some of the low-level types, ID, string, and Boolean. If we look inside post, you'll see we have ID, title, and then author is related to a user, and then comments is related to an array of comments. I can click into user as well and see all the types for that, and the same for posts. If we just quickly look at the backend code, this is our schema. So we've defined types for user, post, comment, and then we have types for the queries themselves and all of the mutations. So here we have get posts returning an array of posts, get post which takes a single ID and returns a single post, and then create post which takes the title and the user ID and again returns a single post. I'll go into more detail on this syntax in the next video, but I just wanted to give you a quick overview of how the contract between client and server works. So let's look at the schema in more detail. As mentioned before, we have the user type, the post type, and the comment type, and then the types for our queries and mutations. So when you're defining a new type, you always use the type keyword. So I could define a new type here called customer, and then give it an ID, a name, just like I have with the other types. There's a few core types in GraphQL. We have string, we have int, we have Boolean, and we have ID as well. We also have this array syntax as well. So if you're going to return an array of types, you can just wrap square brackets around that type. You'll also notice this exclamation mark after some of the types, and that means that the type is always going to be returned, so it's required. If I omit this, it would mean that the type is optional. So on the front end, if I were to request the ID, it could be ID or it could be undefined. Whereas with the exclamation mark, it's always going to be the ID type. With the array syntax, you'll see that we have the exclamation mark twice. The reason for that is if I remove the first exclamation mark, the type now is an array of posts or undefined. If I put this back and then remove the second, it could contain posts or it could contain undefined. So if you know that it's always going to be an array and it's always going to contain posts, you use 2 exclamation marks. For related data, we simply just refer to the type that it's related to. So in our case, we have author here, which is of type user. So anytime on the front end we request an author, we're going to be returning these fields of user. Now let's have a quick look at the resolvers that are actually handling the code. Here we have our resolvers, which are basically a one-to-one mapping to the schema. And these are just functions that get executed every time we call a query or mutation. So in the case of our query get posts here, we have a matching resolver for that. So we've defined the object query, and inside we have get posts, which is just returning all of our posts. We have get post as well, which takes an ID and returns a single post. And inside our resolver, we have get post. The argument it accepts is an ID, and then it returns a single post. In this small example, we're just using dummy data, but in reality, you'd probably be connecting to a database within these resolvers. Let's look at one of our mutations. So here we have create post, which takes the title and the user ID and then returns the new post. So in our resolver, under mutation, we have create post. The arguments it's being passed are title, user ID. It creates that new post, pushes it to our mock data, and then returns the new post. We can also define relationships as well, as mentioned before. So in the case of post, it's related to both author and comments. So back in our resolvers, we define the type post, and then we write the code to work out how this relational data is connected. So in the case of author, we just find the user with the parent's user ID. So in this case, the parent would be the post. And then the same for comments. We return all of the comments where the comment's post ID is equal to the parent ID, which again would be a post. So if I look at the structure of our dummy data to explain that more, we have users which have ID and name, posts which have ID, title and user ID, and then comments which have ID, content and post ID. So effectively these would be foreign keys on our database. So just because these keys exist in our data does not mean we need to return them from our schema. So in the case of comments, we have ID and content and then the post ID. When we define that type within our schema, we just have ID, content and then post. We don't return the post ID itself. That's just for the backend to use to be able to work out the relationship. Hey guys, so in the last couple of videos, we looked at the absolute basics of GraphQL, and now in this video, I want to explain what we're actually going to be building for the main section of the course. So we have a mock application here called GraphHire, and it's basically a mock job board. And we're going to be implementing all of the features to be able to do things like search, applying for jobs, creating jobs, viewing our applications, that kind of thing. So I'll take you through some of the features and then explain what we're actually going to be doing to develop these features. So looking through the first section, we have all of our jobs listed, and we have a search bar at the top. We can run a search, and you can see on the right that we're actually sending requests to our server. So for every key press, a request gets sent to the server. We can apply for jobs as well. So if I click apply here, we'll get a modal coming up for confirmation. I can click apply again, and you can see on the right we get an apply for job mutation being sent. Instantly as well, we get a state change, which means we're doing some local cache management here to get optimistic updates into our application. If I switch over to the applications view, you can see my user profile plus all of the jobs I've applied for. I can also cancel that application at any time as well. And then you'll see on the main search page, the awaiting response status has disappeared. If you're logged in as an admin, you can see all of the jobs that you've listed or created in the past. We could remove those if we like, and we can create brand new jobs. So we can just fill in this form, hit create job, and we'll get a new job listed on the search page. There are two separate user roles as well. So I'm logged in as an admin at the moment, but you can log in as a regular user. So I'll just do that now. So as a regular user, I can still see the job search section and apply for jobs again. But you'll notice that the admin section has now disappeared. So depending on the user you log in with, we have different roles and permissions set up so that user can perform different actions. And that includes seeing different UI on the front end and having different permissions on the back end as well. So when working on this application, all of the code other than the GraphQL part is going to be done for us. So you don't have to write any UI or deal with any React code aside from using things like hooks to interact with our GraphQL client. And again, on the server side, things like database migrations and all of the server setup is done for us, except from the GraphQL part. So we're going to go into this application, set up a brand new GraphQL endpoint, create and design all of our resolvers, and then switch over to the client and actually consume all of those resolvers, and then work on things like cache management, authentication, and all that good stuff. So rather than just looking at irrelevant examples, I thought this would be a really good way to learn through practical and realistic software development. So in the next few videos, we're just going to jump in and start building out all of the features of this application. So I'll see you in the next video. Okay guys, so once you have the source code downloaded, we do have a README file which just goes over some of the basics of the application. We're using npm, so you can install all of the dependencies with npm install. You can also start the server with npm run start. In the package JSON, you'll see we have 3 commands for starting our server. The first is start client for running the client-side React app. The second is start server for running the server-side Node.js application. And then we have a single start command which uses a package called concurrently to run both the client and server. In this part of the video, we'll be looking at the server side only, which is at server/index.ts. So now let's jump in and start implementing our first GraphQL server. So in the server directory, we have the index file, and at the moment, we just have a very basic Express application. We're listening on port 4000 and then returning a message, hello world, at the root. We'll continue to use Express, but then import Apollo as well, and then link the two together so we can serve a GraphQL app on port 4000/GraphQL. So the first thing we need to do is import the GraphQL server. So we're going to be using Apollo server in this course, and the main reason for this is that Apollo is the most popular GraphQL server and likely the one that you would be using in the workplace. So if you end up using a different server like Yoga, the patterns and skills that you learn in this course will be completely transferable. The type of server you end up using is purely an implementation detail. So with Apollo server in place, we also need to import an Express middleware to be able to connect Apollo with Express. So from the Apollo server package, we import a new function called Express middleware from /express4. We'll also need to support cores in this application because the server is going to be running on port 4000 and the client on port 3000. Since this app also supports authentication and user roles, we need the cookie parser package. This will allow us to send cookies back and maintain login sessions. Now with these packages in place, let's define a new GraphQL server. So we say const server equals new Apollo server, and then we'll define empty type defs and empty resolvers at the moment. Inside the start server function, we can then just start our GraphQL server with await server start. And now we can get rid of this app.get endpoint and replace it with app.use. App.use is how you define Express middleware. So we're going to say that on the endpoint /GraphQL, we'll implement all of our packages. So the first we have is cores, and let's define the origin here to localhost 3000. And then we'll also pass credentials true so we can store and send the correct headers and cookies. We'll supply the cookie parser package, then express JSON because our GraphQL server will always respond with JSON. And then we finally pass the Express middleware package and then pass our GraphQL server in. So this is the basic setup to run a GraphQL server. Now let's implement some example type defs and resolvers so we can run a basic test to see if our server's working. So we implement an example query called hello, which will return a string, and then the matching resolver for this, which returns the message, hello world. Now with that saved, we can run our server. This will launch our GraphQL server on port 4000/GraphQL. If we click this, we'll be presented with the Apollo GraphQL playground. We have our query hello. I'll run this and we get the message, hello world. So with this in place, we have everything we need to start building out our real GraphQL server. So in the next videos, we'll delete our mock type defs and resolvers, and then start to implement the real type defs, resolvers, authentication to start building out our application. So in the last video, we set up our TypeScript server and we added a mock schema here just to test that the server was working. But the way we implemented this is not scalable at all. If we had many complex relationships between different entities, how would you actually manage this in a single file? It would just be very difficult to think about that. So let's look at the actual types we would add to our application in the case of this job board. We have users, jobs, and the company. So a user could be a normal user or an admin. They can apply for jobs or create jobs. The job itself can be linked to a company like Google or Facebook, for example. And then in the case of admins, the job would be created by a user. So you can see only with 3 entities, we have quite a complex array of relationships that can occur. So how would you actually design your schema in a way that's actually manageable to think about? What we can do is split each of these types into different modules that only care about their direct relationships. So in the case of user, we have all of the user fields and the fact that a user can apply for many jobs. So we do not care about the company entity in that case. So all of these relationships can be removed. And also the fact that job links back to user is also irrelevant for user. So when we're looking at just the user entity, all we care about is this one relationship. In the case of job as well, we have 2 relationships going out. One to say who the job was created by, so that goes back to a user. And then one relationship going to the company. In that case, we don't care about this relationship or this relationship, which makes job far more easier to reason with. And then in the case of company as well, we only have one relationship going out. So company doesn't need to know that user exists or care about user, so we can delete this and delete all of these relationships. And also we don't care about the relationship from job to company. So when we're working on job, this is the only thing we care about. So thinking about your graph in this way, it means that no matter how big it gets or how complicated it gets, because you could end up with hundreds or even thousands of intertwining connections. When you're working on just a single entity, it's really easy to reason with. So let's jump back into the code and start to implement these entities. So let's create a new folder inside the server directory called entities. In here, let's create our first entity and let's do it for company. Now these will be completely encapsulated modules and only expose their internal content through an index file. So we'll create an index.ts. Now the entity is going to be formed of two parts, the resolvers and the typedefs. So we create two different files. First the resolvers and then the typedefs. Now the index file can export all of the things that we want to expose from our module. So in our case, we import the resolvers, the typedefs, and then export those. We'll combine all of these resolvers and typedefs in a single file in a second. Now we have this in place, we can start to implement the shell of our resolvers. So we'll just define an empty shell for now. So we just say const resolvers equals an empty object, and then we can export that. Now we still have an error here because we're importing a non-standard file, a file that ends in .graphql, but we'll fix this in a second. So let's duplicate this module for each of our other entities. So we copy it once for user, and then we copy it again for job. So let's call this one user, and then this one job. So at the moment, these are all identical. They just have an empty resolver, empty typedefs, and a single index file exporting the things we want to expose. Now let's go ahead and fix this type error. So we need to let TypeScript know what a GraphQL file is. So let's create a new folder in server called types, and inside here we'll create a new file called graphql.d.ts. Now here I'll paste in the type definition. So we have declare module any file that ends in GraphQL. The contents of this will be a string, and then we'll export that content. So now TypeScript knows that GraphQL files will actually be a string. So if we go back into our entities, we can see that the error has disappeared and typedefs is now recognized as a string. Now let's combine all of these different entities and create a single schema that we can load into our GraphQL server. So let's create a new file called schema.ts. Here we'll import a module called make executable schema from a library called GraphQL tools/schema. So this is a library provided by the Guild that allows you to combine different sections of your schema so you can work on them as separate smaller parts. We'll then import all of our different modules. So we have the resolvers and typedefs for user, the resolvers and typedefs for job, and the resolvers and typedefs for company. We then create a new constant called schema, which equals make executable schema. We pass in all of our typedefs as arrays, and then all of our resolvers, and then we can just export schema. So now with this file in place, it means everything has been combined into a single schema that we can now pass into our GraphQL server. So in index, let's import our schema, and then we'll replace all of these mock types with our schema. Now you'll notice that with this in place, we still have an error when we run our server. Although TypeScript knows that the typedef file is a string, when we try to compile that code, it will still run into an error. So inside schema, we need to import another library called GraphQL import node. So at the top, we do import GraphQL import node, we'll save that. And now we just have a new error because all of our typedefs are empty. So for now, let's just add the basic type for company. So type company has an ID and a name as a string, we'll save that. And we're still running into the same error. And I think that just means that we can't leave any of these files blank. So let's just define some basic types for user and then again for job. And with this, we'll just get our final error because query has not been defined. And that's just the GraphQL server saying that you need to define at least the root type. So in each of our resolvers, we have an empty query object, and inside user as well, I've just defined a basic type for query, although we haven't implemented this yet. Now with this in place, we can start to follow this framework to then implement all of our typedefs and resolvers for each entity. Now this pattern is really scalable. I've worked on apps with hundreds of different entities, and you follow this kind of pattern, which means all you care about is the single entity and its direct relationships. So it doesn't matter how small or how big your app gets, this pattern is really nice to follow. Now, before we actually start to implement these resolvers, there's two things that we need to set up first, and we'll do these in the following two videos. So the first is generating types for our resolvers. Obviously, we're using TypeScript, so it would be really nice to get type hints as we're coding. And the second is that most of these endpoints are going to need context about the currently authenticated user. So that means we need to configure some sort of authentication system. So in the next two videos, we'll do code gen and then auth via GraphQL context. After that, we'll then come back and start to implement the actual code for each of our resolvers. Now, before we actually start to implement our resolvers, it would be great to get TypeScript types based on our schema. This is another module that's provided by the guild, and it allows us to generate TypeScript types based on our GraphQL schema. So let's start by creating a new file called CodeGen at the root of our project. So we do codegen.ts. So the first thing you want to do inside CodeGen is import a new module called @GraphQL-CodeGen/CLI. And we're just importing the CodeGen type so that when we type our config, we'll also get type hints for this as well. So let's define a new config, const config, and then give it the type CodeGen config. And the first prop we need to add is called schema. And this just tells CodeGen where all of our GraphQL type defs are. So we're saying that inside the server repository, within any folder, any file that ends in GraphQL will contain our type defs. The second thing we want to do is define an object called generate. Now this is going to tell CodeGen what to actually generate. We'll say, let's generate a file inside server, inside types, called resolvers types ds. This means that when CodeGen runs, it will generate a file in this location. We'll import two plugins, TypeScript and TypeScript resolvers. Now CodeGen has many different use cases, but in our case, we're just generating TypeScript types for our resolvers. So these are the two packages we need. We then define an object called config, and inside config, we give it a default mapper of partial t. And this just means that when we return values from our resolvers, we don't need to return the entire value that is specified in our schema, because some of those values might be returned from nested resolvers. That will make more sense as we start to implement these resolvers. And then finally, let's just export our config. We'll hit save on that. And then inside package.json, we already have a script for running CodeGen. So it's just called CodeGen. And that runs GraphQL CodeGen, pointing to our codegen.ts file. And then we also have a command to generate some Prisma types. Obviously, because this is just a GraphQL course, this part isn't too important, but it's quite nice to just have it all as a single command. So let's just run npm run CodeGen, hit enter on that. That will go ahead and generate our types. Now inside the types directory, we have a new file called resolvers types, which contain all of the types based on our schema. So here you can see types for company, job, all of our queries, the me query, and then user here as well. So if we go into one of our entities now, let's look at user because we have a query for this. Let's add resolvers to our object. So the first thing we want to do is import our resolvers from the generated file. So we import the object resolvers from our new generated file, and then we add it to our resolvers object. And this means that this object is now fully type safe. So I can start to write M, and it will give the recommendation for the me resolver. This already knows as well what needs to be returned. So it already knows that a partial user should be returned. So I can just return a mock user in this case. So I've got the type hint for ID, which just needs to be a string, and then we have no more errors. If I were to return a number here, you'd see we get a type error telling us that the ID is a number when in fact it needs to be a string. So moving forward, we can apply this resolver type to the resolvers in job and inside company as well. And now we can write all of our resolvers with full type safety. Now, the final piece of the puzzle for setting up our GraphQL server is the context object. In GraphQL, context is the way to share data between resolvers. So that means if we need to access something like the authenticated user in a get user resolver or a create job resolver, we add it to context so it's shared throughout all of those resolvers. It's also used for security reasons as well. So later on when we're working with Dataloaders, context is instantiated for every single user request. That means there's zero risk of leaking data between requests. So if you need something that is specific to a user, like an authentication cookie or Dataloaders, then context is the way to go. So in this video, we'll create our context object. We'll update CodeGen types to include the new types for context, and then I'll show you a quick example of using it in one of our resolvers. So let's jump in. So in server, we'll start by creating a new file called context.ts. And in our context, we need to do two things. One, be able to access our database, and two, be able to get access to the authenticated user. So we'll add all of the logic for these 2 points. First, we'll import all of our modules. So the first is Prisma Client, which we'll use to access our database. The second is some types from the Express server. We'll need these in a second. Third is the JWT module, so we can create JSON web tokens for our authentication system. And the fourth is Zod, so we can validate our JWT as well. Next, let's create a function called createContext, and the request and response will be the request and response from Express. We can export this function. Now let's also define a type for our context. So here we have our type context. We'll be returning a Prisma client to access our database and an auth object. This will include the user, which we access from our JWT, including the user's ID and if they're an admin or not, and then some helper functions to log in and log out the user. We'll be working with the cookie module to do this. Next, I'll add a helper called parse token. This will take our JWT token, verify that it's valid, and then finally check the actual payload content with Zod, and if that passes successfully, we'll return the payload data. We'll be using this in a second. The final thing to define is our Prisma client. So we say new Prisma client and assign that to a variable Prisma. So let's work on the authentication part first. We define a new variable called token, which is coming from our request, cookies, and token. We then get our user from the token using the parse token method that we just defined above. Finally, let's return a new object. And let's also just ensure that our createContext function is returning a promise of context. So here we'll add auth, we'll supply our user object. Then let's just add a function to log the user out. We'll do this by calling clearCookie, which is on the response object. We'll then define a new function login. This will accept arguments ID and isAdmin. We'll be calling this from our resolvers to actually log the user in. First, we create a new JWT and assign that to the variable token. Then we respond with a new cookie called token, passing our token in, and then setting some arguments for our cookie. So the domain in our case will just be localhost. We'll expire it in 1 week and make sure it's HTTP only true, so the cookie can't be accessed in JavaScript code on the front end. Now we also need to define our JWT, so at the top of the file here, we'll just define a JWT equals your secret key, and I've just put a comment here as well to say that, in production we'll always use this as an environment variable, but just for the case of this demo we'll just set it to a static string. But please don't do this in production. Just set up environment variables as you normally would with any kind of server. Now the final thing to do is to return our Prisma object, and with that in place all the errors have gone away, and now we have a complete context object. Now you'll notice at the top of the file we're exporting our context type, and that's because we're going to need it for CodeGen. So in our CodeGen file, in config, we'll add a new argument, context type, which refers to the context file, and then we'll grab the context type from that. I'll save that and then run CodeGen again. And this will mean that context is now available in the types for our resolvers. So if I look inside the user resolvers, the first argument is always going to be root, the second is args, and the third is context. If I hover over context now, you see we have type context, which means in every single resolver, we can access Prisma and do things like find specific users, or if the endpoint is authenticated, I can do context or user is admin. I could put a condition around this, for example. So if the user is not an admin, I could throw an error. And this is how we're going to do roles and permissions moving forward. So now pretty much everything is set up so we can start implementing all of the resolver body logic, and we'll do that in the next video. But before we finish, there's just one more thing to do. So back in the entry of our server, we just need to actually include the context object in our GraphQL server. So at the top, we'll import our new context. So import createContext from context, and then down here, we define a new object called context, and it has two arguments being passed in. Since this is coming from Express, we have the request object and the response object. We then call createContext and pass in our request and response. So I'll hit save on this, and our server setup is fully completed. Hey guys, so in all of the videos up until now, we have just been working on the server setup, but now all of that is in place. So we can start to focus on implementing the actual business logic for our resolvers. So this video is going to be quite a long one because we're going to go through each of our entities, company, job, and user, define the type defs for them, and then go back and implement all of the business logic for the resolvers. In most of the resolvers, we're going to be following very similar patterns, just authenticating the user, sending a request to our database via Prisma, and then responding with some data from the resolver. Although that part is not necessarily GraphQL, you're going to start to understand some really interesting patterns of how we actually implement our logic. Even if you're not following along line by line, I think this is a really important one to start to see how you can actually develop a production application in real life. So let's just jump straight in and we'll go to company. Now in company, we're basically already done because in our application, we don't have anything to relate to company. We have just our ID, which is of type ID. We have the name, which is of type string. And the resolvers for this, we don't need to implement any. If in the future we were to have a company page that listed all the jobs related to a company, maybe we could start to add resolvers here for that. But for now, there's nothing left to add. Jumping over to the job schema, all we have at the moment is a job type and we've defined an ID. So let's start to implement all the different fields for job and then the queries and mutations as well. So the next field we need to add is the title, and this will be of type string. Following this, we need our first relationship, which is the company. So we type company and relate it to a specific company. Although we haven't defined this type in this file, because our schema is stitched together inside the schema file, GraphQL will know how to reference company when we start our server. So for now, let's just add company equals of type company. And this is how we define relationships. The next type is just going to be location of type string. Next will be the job description of type string as well. And then we have type, which is a new type called job type. And we haven't defined this yet, so let's just do it now. At the top of the file, we create a new type called enum. So just how you would define enums in TypeScript, you can do a very similar thing in GraphQL as well. So we say our job type enum can be full-time, part-time, or internship in this case. So this is pretty good if you want more strict typing because string can be pretty loose. And since this will map directly to types in our database, it's a really nice one to have. Our next type will be remote, and that will just be a Boolean to say, is the job remote or in office? The next will be salary, and that will just be a flat integer. The next two will be created at and updated at, and these will be of type datetime. Now this type is not built into GraphQL by default, so we will have to go and define it in a second. There are tons of libraries out there to install many of the common types, but in our case, for the purpose of understanding how the system works at a core level, we're going to implement the datetime type ourselves. The final type is going to be another Boolean, is applied, and it will relate to if a user has applied for a job. Now this is not going to be saved against the database. What we do have inside our Prisma schema is a relationship between job and user called applicants. So every time a user applies for a job, there'll be a record stored in the job applicants table, and is applied is going to be a nested resolver that reads from that table and check if a job application has been made, in which case it would return true or false. So let's just keep that in mind for now and we'll implement the resolver shortly. Now these are all of our types for job, so let's define the queries and mutations. To define a query, we say type query and then use the curly brackets. And here we can define all of our different queries. So our first query will be a type called search jobs, and this will allow us to send a query to be able to search for all jobs. So when we looked at the example application at the start, you saw there was a search bar. We could click into it, run a search, and that was executing this search jobs query. So here we're going to learn a common pattern that we will implement throughout the rest of our queries and resolvers, and that is using input types. So if our GraphQL queries or mutations have input, we can define as many arguments as we like. So in the case of search, for example, we might want to search for title or company. So we could have a title input, which could be a string, and we could have a company input, which could be a string, and then maybe location as well. Now, this isn't always the best pattern because when we are executing our queries on the front end, anytime we make a change here, it means we also have to make a change on the front end. So it kind of creates double the work for us. So the better way to do it is to always just define one input type, and we'll call it input. The pattern we'll follow is we'll say the name of the query or mutation. So in our case, search jobs, and then we'll use the word input afterwards. And in our case, this input is required. Now we can define the search input. So we say input search jobs input. Now we can define all of our arguments here. And what this means is if we add an extra argument in the future, we don't have to change the input type here. And it means the front end query never has to change as well. We can just regenerate all of our types, and then TypeScript will work out what arguments are needed to be passed in. In our case for search, all we want is a single argument called query, and this will be of type string, and it will be required as well. So looking at the return types of search jobs, we'll be returning an array of jobs, and you notice we have the exclamation mark twice. So that's saying we will always return an array, and that array will always contain jobs. Now let's define our mutations. So we say type mutation and then use curly brackets again. Now we're going to need 4 different mutations: one to create a job, delete a job, apply for a job, and cancel the application. So we'll follow the same pattern as with search jobs. So we'll have a mutation create job, which takes an input of create job input and returns the newly created job. The next will be delete job, which has a single input again of delete job input, and this will return a boolean. In this case, we need to remember the job won't exist anymore. There's many patterns you can follow for this, such as returning what the job was anyway with maybe a deleted flag, or just return a boolean, in which case we'll do a little bit of cache management on the front end, but we'll get to that later. Our next mutation, apply for job, will also just return a boolean to say the job was applied for, and then cancel application will just return a boolean as well. So you can see for all of these mutations, we have a very similar pattern for the inputs. Now you may be wondering why I'm returning booleans here rather than the job itself, and that's because the mutations here are very predictable. There's not really a need to return any data. When I apply for a job, if the mutation works, I already know what to do on the front end, and same for cancel application as well. So let's actually define all of our inputs for these mutations. We'll start with the create job input. So we define a new input called create job input. In here, we'll define all of the inputs. So the data we want to save against the job will have title as a string, location as a string, description as a string, type, which is again going to be our job type, remote as a boolean again, salary as an integer, and company name this time as a string. So you'll notice here we're not passing in company, we're passing in company name. In our resolver, we'll create a brand new company using the company name and then link that to the job. Our next 3 inputs are all going to be the same. They'll just take a single ID, being the job ID. So we'll have our input, delete job input, taking an ID, then the same for apply for job input, then again the same for cancel application input. So this is everything we need for our job entity. We'll go on to the user schema next and then go back and start to implement the resolvers for these entities as well. Going into user, all we have at the moment is a user type with ID and then our me query, which will access the currently authenticated user. So the extra fields we need for user are email as a string, name as a string, role, which is a new type user role. We'll define this enum in a second. Applied jobs, so these are all the jobs the user would have applied for, and we're going to return an array of jobs here. And then owned jobs, so this will only be relevant in the case of admins, but anytime an admin creates a job, we'll return it from this field. So at the top of the file, we'll define a new type called user role, and this will either be of type admin or user. The me query is already complete. We'll already know who the authenticated user is based on the cookie, so we don't need to pass any data in. What we do need though is some mutations to actually sign the user up, log them in, and then log them out again. So we'll define a new type called mutation again, and then in here we'll define all of our mutations. The first one is sign up, and then following the same pattern as before, we have sign up input, and then we'll just return the newly signed up user. We have login with login input, and that also returns a user. And then logout doesn't require any input at all, and we'll just return a boolean. Now we need to define the inputs for these fields as well. So we have a new input, login input, and this will take 2 fields, email and password. Then we have the sign up input to create a new user. This will again take email and password as strings, and then the user's name and what role they wish to sign up as. So user, a regular user, or an admin. Now with all of this in place, the schema is finished for user, job, and company. So we can go back now to job and we'll implement all of the resolvers. But before we start, let's go ahead and run CodeGen again so we can get full type safety when we're writing our resolvers. So I'll go back into terminal and I'll run npm run code. Now you notice we get an error here, and that's because we've defined this custom Scala datetime and we haven't defined it anywhere. So let's go ahead and define the datetime Scala. So let's create a brand new folder inside server called Scalas. Now here we can follow a very similar pattern as we did for our entities. So that means we'll define a single index file, then the type defs, and the actual TypeScript code for our custom Scala datetime. So we create a file called datetime.ts. In our index file, we'll export these files in the exact same way as we did for the entities. So we import our type defs from typedefs.graphql, Then we import the date time type. We haven't defined this yet, so we're getting an error. Then we'll create a new object called resolvers. So here, if you were to add many other scalas, you could add them to this list, and then we'll just export that. So we export the type defs and the resolvers. Now the type defs for this are going to be super simple. We'll literally just say scala and then date time, and then just save that. And here is where we'll actually implement the logic for this. So being able to convert a basic type like a string to a date and then back again. So the first thing we want to do is import two new types from the GraphQL library. They are GraphQL Scala type to define a new Scala, and then kind, which we'll use in a second. We'll export a new constant called datetime, and that will be equal to a new GraphQL Scala type. We'll give it a name and a description, and then we need to implement 3 fields to be able to convert our value from a date to a string, and then from a string back to a date again. Because when this is serialized as JSON and sent over the wire, we're not actually going to be sending a date, we'll send a string. So we'll create a new function called serialize. This will turn our value into a string. So we'll say here, if the value is not an instance of date or not of type string, we'll just return null because we can't work with that. Then we'll say if the value we receive is a date, we need to serialize it. So we say value to isostring. If it's already a string, then we just return the value. Then we define another method called parseValue, and this is going to turn the string back into a date. So when we receive data back to our GraphQL server, this will convert it back to the date. So we say, if the type of value is not equal to a string, we can't work with that, so we return null. Otherwise, we return a new date from our string value. We also need to define a third method here as well called parseLiteral. And the reason we need this is because if the value is hard-coded in a GraphQL query, i.e. like not used as a variable, we need to be able to parse it back to a date as well. So this is again for data incoming to our server. AST here stands for abstract syntax tree. We'll say if the AST kind is equal to a string, then we'll create a new date. Otherwise, we'll just return null because again, we can't work with that. So if we hit save on that, we can then bring this Scala into our schema. So just as we imported the entities here, we can also import the Scala types as well. Let's just do that at the top. So again, we'll follow the exact same pattern as we did for our entities. So we import our type defs and our resolvers, and again, just load them in the exact same way. So our Scala type defs and our Scala resolvers. Now with that in place, I can run CodeGen again, and now this will work. So now we have full type safety to implement all of our resolvers. But let's just take a quick break there, and then we'll come back in a second and implement all of the business logic for job and user. Okay guys, so we are back for the second section of the schema and resolver implementation. Now, a lot of this video is just going to be implementing the business logic for our resolvers, but we're still going to see quite realistic examples of how we develop GraphQL resolvers and make use of things like context, so we can authenticate and authorize our user and the data we return from the resolvers as well. So how do we actually implement the relationships such as is applied, or on the user, the relationships like applied jobs and own jobs. We'll learn all of that in this video. Now the actual parts where we're calling our database by Prisma, that's not too important for the context of this course, but I'll quickly just go over the Prisma schema to show you the shape of the data, and then it will make more sense when we're actually implementing the resolvers. So our user has ID, email, password, name and role, and then we also have the applied jobs and own jobs, which is a relationship to job. And then we have pivot tables here, job applications, and then job owner. Inside company, we have ID name, and then again linked to jobs. Then inside job, we have all the fields we were familiar with, so ID, title, location, description, type, remote salary. Then it's related to a company via the company ID, and then again related to a user via the owner ID. And then anytime a user applies for a job, we'll have a record stored in the job applications table. So this is almost a one-to-one map into our GraphQL schema, but it is a little bit different. So you'll see now how we actually manage that difference. So let's start off by implementing all of the user resolvers. So me is an interesting one because we need context on the current user. And we already have that because in one of the previous videos, we worked on our context, which will return our user. And then we have these helper methods as well, log in and log out. So let's implement a new async function for the me resolver. We'll say async and then use an arrow function. We have root, which is not relevant here, args, we don't pass any in, and then context, we will need this to grab the authenticated user. So the first thing we want to say, if there is no authenticated user, then let's just return null. The second will be a call to the database to grab the authenticated user. This is just using the Prisma API. So we're saying, let's get the user, find a unique user. where the ID is equal to the context.auth.user.id. So this value would have come from our cookie. If that user does not exist, then we'll just return null, otherwise return the user. Now we've got a couple of errors here that we need to fix. One is that we're returning a user from Prisma. So this is not an exact mapping to our user type defined in GraphQL, mainly because the user role is a different enum. There's a couple of ways we can fix this, but in our example, we're just going to cast the enum value. So we're going to say let's spread user, and we'll say role, which is the user role, and then we'll cast it to user role, which comes from our generated types. So this is going to be the exact enum from our GraphQL type defs, this one here. We're left with one remaining error because we've said in our schema that we'll always return a user, but that's actually not going to be the case. If there's not one authenticated, we're returning null in this case. Let's go back to our type defs, remove this exclamation mark, and then regenerate our types. And now the error's gone away. Now that's the only query that we need for user, so let's just go ahead and implement the mutations. So we use the mutation key, then we add a new function called signup, and then we're going to take all of our input. So we'll say args.input, we're going to get the email, the name, the role, and the password. So this is going to come from our input type here. Then we make a call to Prisma to actually create that user in our database. And just to mention, I'm storing the password as clear text. Now, obviously you would not do this in a production application. So please hash your passwords and follow standard security procedures. But for this example, it just allows us to not get distracted by anything non-GraphQL. With the user created, we can now actually log the user in using our helper from context. So inside context, we have this login helper that gets given a user and then creates a cookie. So in our resolver, we can call that. We say context.auth login, we pass the user's ID, and if their role is admin, we then just return the user using the same pattern as we did earlier by casting the user role. We'll then implement another function, login. So we define a new resolver login, and then we'll take our inputs, email and password. Then we'll use Prisma to try and find a user with that particular email. If the user doesn't exist, here we'll throw an error, and we'll do a very, very rudimental password comparison. And if the password doesn't match, we'll throw an error. If we get past this, then it means the password was a match. And again, we can call our context helper login, pass in again the user ID and the user's role. And then finally, we just return the user in the same way as the other resolvers. Now we need one final resolver for user, and that is logout. So we define a new function called logout. And this is super simple. We're just going to call our context helper context.auth logout. What that will do is clear our cookie, and then we just return true. And that is all of the queries and mutations for user complete. But there are a few more things we need to implement as well. All of the relationships. So we have these applied jobs and owned jobs that need to be implemented. And the way you implement these relationships is we'll go back into our resolvers and we'll specify the user keyword. So here we'll implement only the direct relationships to user, which are the two we just mentioned. So inside user, we can implement two new nested resolvers, one for applied jobs, one for owned jobs, and the names will match the names here exactly. So we define a new function, applied jobs. Here, rather than saying root, we're going to be grabbing the user. So anything that we return from these root resolvers, so sign up, login, me, will be passed into these nested resolvers. So here we'll have a user with an ID, and then we can just send a Prisma query to say, let's grab all of the jobs where the user is an applicant. We can do a very similar thing for owned jobs as well, but there's a slight difference here. So we define owned jobs, but because this is only relevant for admins, we can say, if the user is not an admin, just return an empty array, because a regular user won't be able to own any jobs. We then just execute another Prisma query to say, grab all of the jobs where the user matches on the owner ID. So you'll notice that we have a couple of errors here, and that is again because the types between Prisma and GraphQL don't quite match, but we're going to fix these in a slightly different way so you can learn both patterns, but we'll do that when we start to work on the job resolver. So with this in place, the resolvers for user are now complete. So let's start in jobs by implementing the search jobs resolver. So for this query here, search jobs, we'll define a new resolver again called search jobs. And here we'll just get the arguments, which is going to be the query. So we get the query from input. Then we just send a request to Prisma to say, let's get all of the jobs where either the title or the location are equal to the query. We can then just simply return the list of jobs. And you'll notice that we're getting the same error here as we did with user. And again, that's because the job type between Prisma and the GraphQL don't quite match. So rather than do any casting, I'll show you a different way to fix it. We can go into CodeGen and we can add a new config item called mappers. And we'll add 2 new maps, one for job and one for job type. And what this is saying is every time you come across job, refer to the type from Prisma, and the same for job type as well. So we're going into the Prisma library and pulling out the job type. If I save this and then regenerate the types, you'll notice both of our errors now disappear. So let's continue on and we'll implement the create job, delete job, apply for job, and cancel application mutations. We define a new key, mutation, and let's create a new resolver called create job. Here we'll get all of the input to create our job. But first of all, this endpoint is only accessible to admins. Only admins can create jobs. So we access context again and say if the user is not an admin, then let's throw an unauthorized error. The next thing we do is access all of our input arguments. So title, location, description, type, remote, salary, company, name. Then again, we'll send a database request to Prisma with all of our types. So I'll call context, Prisma, job create. I'll pass in all of our arguments. And then for company, I'll create a brand new company each time. And then for owner, I'm going to connect it to the currently authenticated user. I am brushing over the Prisma stuff quite quickly because I think it's important that we keep the focus on the GraphQL part. Obviously, if you want to implement any of this stuff in your own way, please go ahead. The final thing we'll do is just return the job. We'll now implement the delete job mutation. Here we'll check if the user is an admin again. Then we'll delete the job. And then finally, just return the Boolean true. We'll then implement apply for job. Here the user must be logged in to access his endpoint. So we check on context. If the user is not logged in, we throw an error. We then send the request to Prisma so the user is marked as an applicant against the job using the user ID from context. And then again, we just return true. The final resolver here will be cancel application. So we define cancel application. Again, the user must be logged in. So we do the same check. If the user is not logged in, we throw an error. We then disconnect the user from the job applications using Prisma and then return true again. Now this is all of our queries and mutations for job finished, but we need to implement 2 nested resolvers. So we have a company relationship here. And then for is applied, so this is not going to come from the database. We need to implement some logic in the backend to work out if a user's applied for a job or not. So let's go back into our resolvers. And just like we did for user, we'll define a new key here, job. So for company, we'll define a new relationship, company. And then here, now we made that change in CodeGen, the job being returned here is not going to be the GraphQL type job. It's going to be the Prisma type job. So that's just something to be aware of. With the mappers in place, the data we return from here will be Prisma types. And the data we receive in the nested resolvers will also be the Prisma types. So the first thing we do is just find the company, and we can use the job.company ID from Prisma to get that. If the company is not attached, then some sort of error has happened, so we can just throw an error and then just return the company. For is applied, we just define a new resolver, is applied. And again, we have access to job here. We then send a request to Prisma to get that specific job only where the user has applied for it. And we're sending a count query. So now we just need to return. If this count is more than 0, then we know the user has applied for the job. Now, one thing I did forget to do in one of the previous videos is inside CodeGen. We also need to define our scalas here as well. So inside CodeGen, let's just define scalas and then say that our date time is specifically a date. Now we can run CodeGen again, and that will generate new types for us. And now that is the server-side part of the application complete. So following this, we'll actually start to implement these resolvers on the front end. So in the next series of videos, we'll be purely working on the front end and then executing queries to access all of the resolvers that we've just written. Now we're finished with the backend, we can finally move over to the front end of the application. In one of the earlier videos, we demonstrated what the graph hire application looked like when it was complete, but the position we're in now is we have all of the React components complete, all of the UI work complete, but the GraphQL part is completely removed. So we're going to go through, set up our GraphQL client, and then go through each component and add the queries and do all of the smart stuff like cache management and writing our mutations as well. So in this video, it's going to be a pretty simple one. We're just going to configure the Apollo client. And I think I mentioned before, but the reason we've gone with Apollo is purely because it's very likely the library that you're using at work, as Apollo server and client are the most popular tools on the market. There are plenty of other tools like Urkel or React Query, and everything you learn from this course is very transferable to those libraries as well. So don't worry too much if you're using something else in your day job. Now let's switch back over to the code. Now rather than working in the server directory like we were before, we're now going to be working in the source directory where all of the front end code sits. The entry to the application is the index.ts file in source, so this file right here. So if we click into app, we'll see that we have an auth provider set up, but this doesn't really do anything at the moment. So the first thing we need to do here is configure our Apollo client, and then we can start actually implementing some queries and mutations. Inside source, create a new file called client, where our client configuration setup will live. So we create a file called client.ts, and in here we need to import a few things from the Apollo client library. So we need Apollo client itself, the in-memory cache. This is just the most basic version of a GraphQL cache, where everything is held in memory. And then the create HTTP link, which allows us to send HTTP requests to communicate with our GraphQL backend. We'll then say const HTTP link equals create HTTP link. And then here we'll add a few arguments. The first is a URI, which is going to point to our GraphQL backend. So that's running on port 4000 at /GraphQL. Then we'll add credentials include. Because we're doing authentication with cookies, this is really important to have. Then we define our Apollo client. So we say client equals new Apollo client, and we pass the HTTP link into the value link. And then we pass a new instance of in-memory cache to the cache argument. Finally, we'll export the client, and that's the client setup. Now let's switch over to app so we can configure an Apollo provider and then pass our clients in. Inside app, let's import the Apollo provider. So here we'll say import Apollo provider from Apollo client, and then we'll wrap it around our application. And then the final thing is we need to pass the client in as well. So we say client equals client, and then we just need to import that client as well. So let's import client from client, and that is pretty much it. So with this setup, we can now execute queries and mutations in the application. There are many ways that we could send a GraphQL request from our client. The simplest is that we could simply just call fetch to our GraphQL endpoint as a post, because all GraphQL requests are post type, then just pass in the stringified body with the query and variables. But this is a pretty rudimentary way to do it, and we wouldn't make any use of the Apollo cache. So we won't go with a fetch approach. A slightly better method is to use the client directly. So the client that we defined in the previous video, we could just import that and then call client.query, passing in a query and their variables. And then this again would return a promise with our data. But this isn't too useful in the context of React. With React, Apollo provides us a hook called useQuery. We can pass in the same query that we defined here, and then this would re-render as soon as data becomes available or the loading state changes, meaning we don't need to call client.query in any kind of use effect or manage the state ourselves. It's just managed automatically through the available hooks. These two methods as well will also make use of the Apollo cache. So as data gets loaded down to our client, it will populate a cache. And then if we were to re-execute the same query again, it could get the data from the cache instead. All of that is automatic. But although these two are great choices, we're not going to go with either of those. What we're going to do is configure CodeGen just like we did on the server side. So we'll define queries in separate files, we'll run CodeGen, and that will generate for us fully type-safe hooks, which implement useQuery internally. So that means rather than say useQuery and pass in a query, I could say generate some hooks, and then that will give me a hook called use search jobs query, and then this will return the same data as useQuery would, except from it would be fully type safe. So in the next video, we'll configure CodeGen and then start to implement some of these fully type safe hooks across the application. Now let's configure CodeGen so we can get fully type safe hooks in our application. So to actually see it in action, let's just write a single query in our application. So inside source root job board, let's add our first set of queries. So we create a new file called queries.graphql, and in here let's define a new named query called search jobs. We'll then call the search jobs query and then define a new input using our search jobs input that we defined on the backend. So this is the variable input, and then we pass it into our query. So input is equal to the variable input, and then let's return two different fields. So we'll have ID and then title, and we'll just leave it at that for now so we can see CodeGen in action. So let's jump back over to our CodeGen file, which is at the app root, codegen.ts. And at the moment, all we're doing is generating types for the backend, but we can add a new set of configurations so types are generated for our hooks as well. So the first thing we want to do is tell CodeGen that we want to generate a new file called source types graphql.ts. What this will do is introspect our entire schema and then generate a TypeScript file with all of the types for our schema. So we need this first before we can generate the types. We give it the plugin TypeScript, and then we apply a simple configuration, which is just to say that enum values should be uppercase. Now, this is a personal preference of mine for most of my projects. You don't need to include that config. Then the next piece of config we want is to look across all our files within the source directory. So we'll define a new config called source. And the idea of this is to look through every file in source that ends in GraphQL and generate the hooks for us. So to do that, we need a preset called near operation file. And this will allow us to search for all the files, grab the particular query and generate a file next to it or near it. We'll define a new argument called preset config and then give it two arguments. The first is extension to say that whenever we find a GraphQL file, we'll generate a TypeScript file ending in generated.tsx. We'll also need to fetch all of our base types from the file that we just generated above. So we say base types path equals types /GraphQL.ts, which equals the same path here. The plugins we need for this are TypeScript Operations and TypeScript React Apollo. Depending on your setup, you'll need different plugins. For example, if you're using a different client library like Urkel, a different library would be necessary here. We'll define some config for this as well to say that we want hooks. So we say with hooks is equal to true. And then also we need to redefine our Scala type as well. Scala's datetime is equal to a date. The final thing we then need is to tell CodeGen where all of our documents live. So to look for files that end in .graphql. So we add a new key here called documents, and that says look inside source in any folder and any file that ends in .graphql. So that would match against this one here, for example. I'll save that and then let's rerun CodeGen, and you'll see that we have a queries.generated file which contains our search jobs query. And then we also have a hook, use search jobs. Also inside types, all of the base types based on our GraphQL schema are available here, and that would be imported into the generated types. Yeah. So we get full type safety from our introspected schema. In the next video, we'll start to implement these hooks for all of the different components. Okay guys, we have all of the server side set up, and now we have the client side configured as well, which means we can start writing our first query. So looking over at the application, we have this search field here, and at the moment we're not displaying any jobs at all. By the end of this video, we would have configured this section, so I can start typing in a search and we'll actually see values coming back from the server. Before we do that though, let me just give you a quick overview of how the app actually works. So we have this hook here called use search jobs where we'll implement our GraphQL query. Now, in the root of our app, we have router provider, which is given a router, and this just links to all the different pages in our application. So at the moment, we're going to be working on the index screen, which is going to point to the job board route. So in job board, we have our hook, use search jobs. This exports four things: search, set search, which is used to control the search bar. So this guy here. Then we have the results coming back and an is loading indicator. So if loading is true, we'll show a little spinner here. And then the results are being rendered at the bottom. So we're just looping over all of the results and then rendering a job card. So all of the UI part is done for us and we just have to connect it to our backend. Now in the server side section of the course, we have already written the resolver for search jobs. So all we need to do now is to connect it up and then we should start to see results. So let's start to request all of the extra data from search jobs that we need for the results screen. So for this, we need the job's location, then the type, then if the job is remote or not, then the salary of the job. Then we'll load some relational data. So we want to get company in this case, and of the company, we want to grab the ID and the name as well. We'll then get the date the job was created at. And if the user has applied for the job, we'll save that. And then we can run CodeGen, and that will regenerate all of our types into queries.generated. So inside use search jobs, we can now implement this query. So the first thing we need to do is actually import our new hook. So we import use search jobs query from the local queries.generated. So this will be a fully type safe version of the use query hook. We can now remove this mock data and then we can start to implement the hook. We say const, an empty object, is equal to our hook, use search jobs query. We'll define some curly brackets because we want to pass some arguments into our query. We return two pieces of information, data, so the actual results of the query, and the loading status. We'll need to pass in some variables as well. So we say variables and then is equal to our input. The pattern that we follow is always to define the input as input. Then we pass in our query, which is equal to search coming from the local React state. Now we need to grab the actual results from data, but the data may not have returned yet. So in that case, we always need to be returning an empty array so that the results is always at least populated and we don't get any render issues. So let's define a use memo. Then we'll say, let's get the data.search jobs, otherwise return an empty array. We then need to put the data into the dependency array. So data.search jobs. Data has a question mark here because it may be undefined if loading hasn't completed yet. And then we finally just need to import use memo. Now with this in place, we should start to see some results come back, but first we need to seed our database. So I've already defined a script to seed some data which will match our Prisma schema. Inside package.json we have seed, which will run a script to first remove the dev database and then run migration again, and then insert some seed data. So at server Prisma seed, let's just have a quick look at that. Prisma seed, we just have a script that adds a couple of users, adds some companies, and then adds a bunch of jobs as well. So let's run seed. Now we have some data in our database. Then let's run npm run start. And you see now in our job board, we have results rendering on screen. Now I can search for jobs as well. So I can say UX or dev ops, and you can see results are being sent back to the server. And then the response is showing all the jobs that match on our search term. So if I look inside request, you can see that the search term I typed in is being sent back. And then we're getting all the relevant results that match. You may have also noticed as well that when I'm searching at the moment, there's a bit of a flash on the UI, iOS. And that's because there's a little bit of latency when I'm sending a request to the server before results are returned. So for a moment in time, there's nothing that matches the current search. Now, once a search has happened and then I retype it, the flash goes away because the data has now been stored in the GraphQL cache. And from this point forward, we're looking inside the cache since the cache has some data that matches. But if I refresh the screen and do this again, you see we're back to a flashing UI again because there's no data in the cache on first load. But there is a way we can fix this. So let's go back into our search jobs query. So inside use search jobs hook, in the hook, other than variables, we can also pass some more arguments. And the one we want to pass in is called notify on network status change. And what this will do is give us access to a new argument called previous data. And this is all the data that was available in the previous render, meaning that when we load the page for the first time, if I type something like iOS in, we can look at the current state of data, which could be undefined because we're fetching results from the server, but we can also look at the previous data, which is always going to be in the cache. So here we're saying if data.search has no results, then we'll return an empty array. But instead we can say if data.search has no results, or previous data.search has no results, then return an empty array, and then pass previous data search jobs into our dependency array. And then when we come back and search again, even on first load, we get none of that UI flash, which means that by default, we're checking both the local storage or the local state and sending a request to the server to get the latest results from there as well. Pretty much every other section of the app requires the user to be authenticated. So we can search for our jobs here, but if I try to click apply, then we're presented with a modal telling us that we need to log in first. So this is probably a good point to start implementing our authentication system. So inside of our app, where we implemented our Apollo provider, you'll notice that we already have an auth provider set up. So let's have a look at how this works. Auth provider can be found in providers/auth provider on the source. And in here, we have a basic React context. So we have some values already defined, one for the user, if the user is still loading, if there was an error, and if the user is logged in. We have some empty functions here as well, sign in, log in, and log out. And these are used in various places across the application. For example, when we click login here, we're presented with a modal, and if we click login, that will call login via our use auth hook. So if I search use auth in the application, you'll see that it's defined in a couple of places. So mainly inside the layout where the header sits. So this main component at the top here, and we're using pretty much all the values from the hook is logged in, user, sign up, login, log out. Inside job board as well, when we apply for jobs, we first need to detect if the user is logged in. If they are logged in, we show them a modal to confirm their application for a job. And if not, we show the modal, please log in or create an account. So that's the one we see at the moment because the user is not logged in. So let's switch back to the auth provider and we'll start to implement all of the GraphQL queries for this. So just in the same way as for job board, let's create a new file called queries.graphql. And the first query we need is the me query, which we can use to check if the user is actually authenticated or not. So we define a new query called me, and we're calling the me query. And from here, we'll return the ID, the user's email, the name and the user's role, so if they're an admin or a regular user. We also need to implement some of the mutations here as well, so to sign up the user, log in the user, and log out the user. So the first is a mutation called sign up, which takes our input, sign up input, and then we call the sign up mutation, passing our input across, and then we need to return some fields here as well. And the fields we need are pretty much, or are exactly the same as the fields from me, but it's not too great to have to repeat these if we know they're going to be identical. So what we can do instead is implement something called a fragment. And a fragment is basically a reusable section of a GraphQL query. So rather than define these fields twice, we just define them once in a fragment, and then we can reuse that fragment in both of our queries. So at the top of the file here, we say fragment keyword. We give our fragment a name, let's just call it user. And then we need to say what data type is the fragment on. So we say on, and then again, it's on the type user. So we have user twice. You could call this anything you like, but it's just simple to call it user here. Then we define curly brackets, and then we say the fields that we want this fragment to include. So it's all these fields here, ID, email, name, and role. So we return them here. I save on that. And now instead of returning the fields, we can just spread our fragment. So it's very similar to the spread syntax in JavaScript. We can do the same for sign up as well. And then we also need the mutation for the user to log in. So we say mutation login, and the input is login input. We call the login mutation, pass in the variables across, and then again we spread user. And the final mutation to log out is going to be a very simple one. So we say mutation logout, and then we simply call the logout mutation. And because this is just going to return a Boolean, we don't have to define any fields. So this is complete as it is now. So let's hit save on that, and then we can regenerate our types. So now we have a newly generated file, queries.generate.tsx, inside our auth provider. And now we can implement these queries and mutations inside the auth provider. So the first thing the auth provider needs to do is to return information about the currently authenticated user. So here we have user, which is currently set to null, but we can grab the information from the me query. So at the top here we say const, and then we'll grab the data, the loading status, and an error status from our hook. We say equals use me query. Let's import this query now. So that's being imported from the local queries generated. And then inside our value here, we can say data, which might not be available yet, .me. Otherwise, let's return null. And the reason we say null is because me could be null or undefined. So we're just kind of reducing it down to a single type. You'll notice our type here for user is currently set to any, but now we have a query generated, we can actually pass the correct type for this. So from our inputs at the top here, we can import the me query types. And then here we can use this. So we say me query, and then from that we grab the response me. Otherwise, we're going to return null. Let's also pass in the loading state here, and then also the error, otherwise null as well. And then if the user's logged in, we can just double check if data has been returned from the me query. So we say not data me. So this is going to convert that to a Boolean. True if there is data and false if there is not data. With that in place, we can now implement the sign up, login, and logout mutations. So let's start with sign up. So here we say const sign up mutation is equal to the use sign up mutation hook, and then we can import this. So this also comes from the locally generated queries, and now we can actually use this sign up mutation inside the sign up function. Now the reason we have to define array syntax here is because the hooks from Apollo always return an array. For mutations, the first argument is the actual function we use to execute the mutation, and then we can also grab some extra data as well, like the loading state, the things that you would get from the queries. So let's implement the sign up mutation. So we say await sign up, and then we pass in our variables, and then again input, and our arguments here we have sign up input is going to be email, password, name, and if the user is an admin. So we say name equals input.name, email equals input.email, password is input.password, and then we don't have an isAdmin, so we say role is input.isAdmin. If that's true, we pass the role admin, otherwise we pass the role user. This can also be imported from our types. So at the top here, we've imported user role from our GraphQL types. Now, because we have the sign up mutation and the me query, Apollo is not going to know automatically how to link these two, because once sign up returns a user, we need to tell Apollo to inject that user back into the me queries section of the cache. So to do that, we can do a little bit of cache management. So in new sign up mutation, we say, once the mutation is completed, let's get the data that was returned from the mutation. So if we look inside our queries, we can see that from sign up, we're returning the exact same data that we returned from me. So we can pretty much assign this data back into the me query, which will mean that when we update the cache, this hook here will automatically re-render and the user and data will be returned from the me query, and then the user will be seen as logged in. If we didn't do this, then the user would sign in, would get a cookie, but would need to refresh the screen for the me query to actually return results. We could also just say, rather than update the cache, we could refetch the me query, but this avoids an extra network call. So in here we say client, and this is going to require the client, which we configured earlier. So the Apollo client itself. Then in client we access the cache, and then we want to write to a query. The query we want to write to is the me query, so we import me document. So again, this is coming from our generated queries. If we look inside here, it's the actual query structure for the me query. So this is how you can target specific queries. Then the data that we want to pass in, so we say data me in this case, and then the data from our sign up mutation. So with this in place, when we sign up and then this function runs, the user will automatically get loaded into this query, and this avoids us having to send a separate network request. So let's implement login as well, which is going to be pretty much identical to the sign up mutation. So let's just copy and paste this, and then we'll call this use login mutation. We're also going to do the same cache update as well. So when the user's logged in, we automatically update the me query. But here the data is going to be login, and then this is going to be the login mutation. Inside login, we can then use the login mutation. So we say await login mutation, and then we just pass the input in directly because it's already a perfect match for what the login mutation requires. So we just look at the types up here. We're taking an email and password. Finally, let's implement logout. So here we say const logout mutation is equal to use logout mutation, and then we can import that as well. And then let's use that inside our logout function. So we just call our logout mutation. But there's another thing we need to do here. When the user logs out, we need to remove them from the cache this time, rather than adding them to the cache. And we can do that by calling cache reset. So we say, once this query has completed, rather than calling write query, we say client cache.reset, which will remove the user from the cache, and then we can redirect to the home page as well. So you could do any kind of local routing here, but in our case, we're just going to update the window.location. If this was to perform a full page refresh as well, this line here would be redundant because when the website reloads, all of the queries would be re-executed. So me would then not return information because the user's logged out. But if you're doing any kind of local routing, or if your cache is not using in-memory cache, you're using some sort of persisted cache, and it just means that when you log out, then any kind of session information is completely cleared up and there's no chance of any kind of data leakage. So with all of this in place, we should be able to now log in. If we go to the README, I've already added some details about the test users that are seeded when we ran the npm run seed script. So we have a regular user here with email user@example.com and then the password 123. So if we just run the app again, npm run start, and then switch over to the browser, we should now be able to log in. So I'll say user@example.com and then password 123, hit login, and that's just a password warning because the password is very weak. But there you have it. We now have the user being logged in, so I can click through to the profile page and all of the user's information is available. At the moment, we still can't apply for jobs because we need to implement that mutation, but at least the app knows now that the user is logged in. So we get in the confirmation modal instead, and I can also log back out again. And you see the header responds to the fact the user's logged out, and then let's just log back in again. So there we have it. That is the authentication system done. So next we'll configure the mutation to apply for jobs and then cancel the application as well. Okay guys, now we're at the point we can search for jobs and we can log in the user as well. So we need to be able to implement the mutations to apply for jobs. So when we click apply here and then apply here, we should send off a mutation to apply for that job. And then inside the profile section, we should see the actual user data and then instantly all of the jobs they have applied for in the past. So here we're at /profile. Now let's look at that component. So inside roots profile, we have our index file, and currently we're just returning dummy data because we're not actually implementing any sort of query here. So we have the information about the user and applied jobs is just an empty array. Now in a single query, we can fetch all of the user profile and the applied jobs. Because if we go back to server and we look at our schema for user, so inside type defs for user, we have the user information plus the applied jobs and owned jobs. So let's go back to the profile screen now and then add a new query here to be able to request the user information and the applied jobs. So we say queries again.graphql, And here we create a new query called profile. And inside here, we are again requesting me. So for here, let's grab the ID, the name again, the email, and then the applied jobs. So we say applied jobs, and we use curly brackets again to get all of the applied jobs. And for applied jobs, we want the ID, the title, the location, the type, if it's remote or not, the salary, the company information, and then again, created at. So we hit save on that. And then again, we can regenerate our types. And now we have newly generated types here. So we have the profile query and the profile hook available, use profile query. So back inside our root, we can now replace all of this dummy data with the actual query logic. So first, let's remove this dummy data. And now we can implement const data equals use profile query. We import that at the top and press save. And now that is everything complete. So this data will feed through to the component profile where all the UI exists. And that will render the user's name, the user's email, and then down here, the actual applications. We have an empty stat as well if there are no applications. So looking back at the profile screen, let's start our server again. So now when we load profile, we can see there is a profile request going out and we're requesting all the information about the user and the applied jobs. Because I haven't applied for any jobs yet, we're still getting 0 results coming back here, but we'll update this in a second. So let's go back to our code and now let's jump over to the job board section again. So this is back on the index page. So looking back at the job search screen, we have inside our job board, there's also a component here called apply dialog. And this opens when we click apply here. So this is the apply dialog. It's a confirmation. So let's look inside apply dialog. We say apply for role, confirm you would like to apply for this role. And then when we click apply, we call the function handle apply. So we need to implement some mutation logic to actually trigger the apply for job mutation here. So we already have some queries set up for this component. So let's go back into queries and add our new mutation. Mutation, apply for job. And then the input will be apply for job input, just following the same pattern as before. And then we'll call in the apply for job mutation. And this returns a Boolean as well, rather than any kind of data. So this query is finished. Now let's regenerate our types again and then go back into apply dialog. And now we can implement this hook. So here, let's implement the hook. So let's say const and then brackets, apply for job. So this is the mutation we will call. And then we also want to grab the loading state. We're using a mock loading state up here. So first let's delete this one. And then we can grab loading from the second arguments. Then we say use apply for job mutation. And now we can call apply for job here. So let's say await apply for job. We already have the job ID being passed into the dialog itself. So we can just use this when we call the apply for job mutation. So we say variables and then again input and then the job ID itself. And that's equal to on input, I think it's ID. So now looking back at the application, we can click apply and then apply for job. This calls a mutation, but we're missing a couple of things. One is that when we look at the applications, it hasn't loaded into the application yet. It would require us to hard refresh the page. And then also in job search, we want to see an is applied icon here. So now the mutations ran, I can fully reload the page and we see the awaiting response. And then also the application is available here. But how can we do this without requiring a full page refresh? The next time I click apply for job, let's see if we can get it to load automatically. So let's go back to our code and again, we just want to do some cache management here. There's a couple of ways we can update the local cache. One is by refetching queries. So in the case of the profile query, which we just implemented, we could refetch this entire query once a job has been applied for, and that will refetch all of the applied jobs. So let's give that a go. So inside our arguments for the apply for job mutation, we say refetch queries, and then we pass in profile here. So we use the string profile because that's the name of the query we gave here. So it's really important that you name your queries uniquely so we can reference them in other places. And then the second thing we need to do is when we click apply for a job, we need to mark that job as is applied. So rather than refetching all of the search queries again, let's use some cache manipulation this time to see how that will work. So we say on completed, let's import the client again and we'll say cache and then let's call modify this time. And the reason we call modify is so we can update a single job in our cache. So we say ID and the ID in the cache is going to be constructed of the data type. So in this case, a job and then the job ID. And then we say fields. So which field do we want to update? We say is applied and then a callback to true. So let's save that. So this will update the exact job in the cache that we've just applied for based on the job ID and mark is applied to true. So going back to our application now, I'll apply for this job. I'll click apply, and instantly, without a page refresh, we get a waiting response because is applied is now being marked against this job. Also in the applicants section, we can see that both of our jobs that we've applied for are here. And if I apply for a third one and then go back without a full page refresh, you can see the jobs are now listed here. So we're making really smart use of the cache and the ability to refetch queries as well to make sure everything is updated on the fly. Now a little bit about the cache as well. So we did some cache modification here against job with a particular ID. Now let's look at the Apollo DevTools. So install this extension Apollo Client DevTools, and then you'll get this little pop-up here, Apollo, and it will show you all the information in the cache. So if I look at cache here, you can see all the information that we have stored. So we have some companies and then some jobs with the particular IDs, and you can see the information stored in the cache for that job. So when we do cache modify, we're saying, let's grab this cache element by this key, and it's always the type name, job, plus the ID itself. So we target a particular job and we say, which field do we want to update? In our case, it was is applied, and we toggled it to true. So when the cache updates, the hooks re-render, the components re-render, and we instantly see the updated data in our application. So in particular, when you're working with Apollo, this is a really useful extension to install because it means you can inspect the cache directly, and it helps with debugging issues and really seeing what's going on under the hood. In the next video, we'll look at cancelling our applications and then looking at the admin section. Now we'll work on the implementation of the cancel application. So in the previous videos, we worked out how you can apply for a new job. On the search section, you click apply for the job, and then that will cause an application to appear here. Now on the profile section, when we click cancel, this modal appears, cancel application. When we click confirm, that needs to send the mutation to the server, then also remove that particular job from the local applications list, and then also remove the awaiting response tag from the job board as well. So let's go back to our code. The section we'll be working in is in root profile. So in our profile page, let's have a look at the UI here. We have this hook being imported called use cancel application, which returns a function, cancel application, and the loading status for that. So looking down at the job card, we have this button here that has the text cancel. That is the button that's rendered here on the application section. So when we click cancel, the modal appears. Back over at the code, this is the modal itself. So this application's modal here. So when the user finally clicks yes, cancel application, we are calling a function returned from the use cancel application hook. So all we need to do is define our new mutation, then call it inside the body of this function, and then update the cache accordingly or refetch any queries so that the local state changes as well. Let's jump back over to queries.graphql, and here we'll implement our new mutation. We'll say mutation, cancel application, we'll give it the input cancel application input, then we'll call the cancel application mutation, passing the input across. And again, cancel application just returns a Boolean, so we don't need to request any fields here. Let's just save that. And then in terminal, we can rerun CodeGen. So this will update our queries generated with the cancel application mutation. Here it is. Now we can call this inside of our customer hook. So first, let's input the hook. So now let's implement this hook. So we'll say const square brackets equals use cancel application mutation. From here, we'll define cancel application mutation, and then we'll also grab the loading state as well. We can return loading rather than just the dummy data here, false. Save that. Now we already have the job ID being passed into the function cancel application, so we can just say await cancel application, and then the variables input, and then the job ID itself. So now with this set up, we can send a request to the server to cancel, but we need to do some client-side changes as well. So the first, let's just format this for 1 second. The first thing for definite we need is to refetch the applications again, just like we did when we applied for jobs. That will mean that when the backend sends the applications back, the application we cancelled will be removed. So that item will disappear from the list. So we define refetch queries, and then we call profile again. Then finally, on the job search page, we also want the awaiting response to be removed from any job on the job board list. And to do that, we can call cache modify again. So we say uncompleted as a callback, we import client.cache modify. And just like we did before, we say ID equals the job ID. This is the exact same structure as we use for applying for jobs. And then we update our fields and we mark is applied to false this time. So let's hit save on that and then run the server again. Now let's open the network inspector and then let's hit cancel, and you can see a cancel application mutation is sent. The profile query is re-triggered, the job has disappeared, and also the awaiting response has been removed. So let's remove these two as well. And there you have it. In the next section, we'll log in as an admin, and then we can work on all of the admin page in one video to list, create, and delete jobs. This is the final video for implementing the front-end logic, and we're now on the admin section. So I've logged in as an admin, and you can find the credentials for that inside the README. So the seeded data includes an admin user, admin@example.com, with the same password, password123. If you log in as a user, you will see the admin section appear on the header. Inside admin, we can have all the jobs listed that we have created, and here's a button which will open a form to create a new job. We'll fill in all of the details, hit create job, and that should trigger a mutation to create a job. Once the jobs are listed here, we'll also have a cancel button, very similar to how applications work. Hitting that will then delete the job, which will remove it from the job search sections and the applications as well, if it's already listed there. Now jumping over to the code, let's have a look inside the admin section. So this is the only section we need to look in, source, root, admin, and I'll just close all the other files. We have 3 files that we need to look in. The first is the index, where the query will be sent to find all of the created jobs for this particular admin, so any jobs that the user owns. The second is the use delete job hook. Here we'll implement the logic to delete a job. And then the third is the create job dialog. So this is just a form using React form. And then when we press submit, we'll call the onSubmit handler, and that will in turn call a new mutation to create the job. So first off, let's create our queries. So we'll create another file inside admin called queries.graphql, just like we did with the other sections. And now in this section up front, I know that we're going to need a fragment. We defined a fragment for user and then used it to fetch the user, sign up the user, and then log in the user. In our case, for admin, we're going to return the same data for fetching the admin query and for creating jobs as well. So let's start by creating a fragment called admin job on job. Here we'll need the ID, the title, the location, the type, if the job's remote or not, the salary, the company information including ID and name, and then the created at date as well. Then we can define our first query. So we say query, just call it admin. We're going to request me as well. This time all we want is the owned jobs, and then we can spread admin job there. Then we can define the mutation to create and delete a job. We say mutation, create job, pass in the input, create job input. We'll call the mutation, create job, pass in the input across, and then spread in admin job. Then finally, we can create one more mutation for delete job. Mutation, delete job. The input will be delete job input, and then we'll just call delete job, which will have no selected fields because again, this just returns a Boolean. We can save that and then rerun our code gen. So now we have a new file inside admin for our queries and mutations, and now we can go across each file and then implement them. So let's start off with delete job this time. We'll remove this dummy data and say const square brackets equals use delete job mutation. Here we'll define the function delete job mutation and also get the loading state, which we can replace the dummy data with here. Then we can call await delete job mutation. We'll pass in the variables input job being the job ID. And then rather than just refetching the admin query, let's try a different cache approach this time, just so we can see a different method in action. Let's say onCompleted as a callback, and then we'll have client.cache. So let's import clients, and then this time we'll call evict. And evict simply removes an entry from cache by its ID. All we need to do here is pass the ID in using the same structure as before. So the type name plus the job ID. Apollo will then automatically remove this from the cache, and then the hooks will re-render and the entry will disappear. So now let's implement the logic to create a new job. When this form opens, we fill in the details, press create job, and that will call a mutation. We can add the mutation itself into the create job dialog, which is this component itself. So let's remove our dummy data, loading. We'll say const square brackets again, use create job mutation this time. We'll define a function, create job mutation, and then get loading. Then inside our onSubmit, we can call await create job mutation, passing in the data from the form. And this is already an exact match for what the mutation needs, so we can just pass it directly across. When the job is created, we can refetch the admin query so the job appears. So refetch queries admin, which will match this key here. So depending on if you choose to update the cache or refetch queries, it's going to be just purely dependent on the needs of the application, but I'm trying to show you all the different methods that you can use. So when you do go ahead and build applications yourself, you have a whole collection of tools to choose from. Now this section's done, so let's just go to listing the admin query itself. So inside admin root, so admin index, we can implement the logic here. At the moment, we have a bunch of dummy data. So let's replace this with the actual query. We'll say const data equals use admin query, and then we already have this set up correctly, data.me.ownedjobs, or an empty array. Let's actually add a use memo here as well, because this empty array will be a new reference every time and could cause excessive re-renders. So we'll just say use memo data.me.ownedjobs, and then passing data in as a dependency. Now with all of that in place, we should now be able to see all the jobs the admin has created, create new jobs, and delete jobs. So let's go back to the UI. We can see already, because of the seed script, all of the jobs we currently have are assigned to the admin that was seeded. The first job here we have is UX designer, and it's available on job search. If I then go to admin and then remove this, we have delete job sent. The job has disappeared, and then also in job search, the job has also disappeared. And that is purely down to the cache evict function that we called. We can also create a new job. So I'll say we're looking for software engineer, job description, let's just say test for now. Test, full time. Let's say it's remote, and then let's say 120,000, create job. And then here we have our test job, which has immediately appeared due to the fact we've refetched the admin query this time. And with that done, this is as far as we'll take the application in the fundamentals section. We'll follow up this with one more video to look at data loaders back on the back end. But hopefully you found that that has covered quite a lot in terms of how we can refetch queries, manage the cache in many different ways, and also how the client itself relates to all of the backend work that we did. Thanks for sticking around to the end of the application build, and I'll see you in the next video. We're going to jump back over to the back end for this final video because we have a notable performance issue that's occurring, and that's coming from the job search section. So we have our job search section here, which returns a list of all the jobs that an admin has created, so all the jobs we can search for, and this comes from the search jobs query. Now, it might not be obvious at the moment what this performance issue is, so let's just jump onto the back end and we can talk through the whole thing. So the first thing we want to do is go into server and into context. And here we have initialized Prisma, and we just want to add some login for this so we can see all the actual SQL requests that are being sent to our database. So we say log, and then we'll log just everything: query, info, warn, and error. So let's save that. And now when we go back to our browser and run this query, we'll see that even though we've sent just 2 requests here, so search jobs and me, the main thing we're concerned about at the moment is search jobs because this is where the issue is occurring. We can see all these SQL requests that are being sent to the database. So the first one here is just to get the current user, so that's not a problem. The second is to get the list of jobs themselves, so return all the jobs. And then all of these requests are triggered by our nested resolver is applied here. So these nested resolvers fire for every single instance of job that's returned from search jobs, because, let me just minimize this, we have our resolver here, job. So for every job that's returned, we're going to trigger is applied, because on the front end inside search jobs, we're accessing the is applied resolver here, meaning that we have the initial jobs query sent and then 10 extra requests sent to the database, resulting in 11 queries. In GraphQL, this is called the n+1 problem, the +1 being the initial query, search jobs, and n being the count for the amount of nested resolvers that are called as well. So we can solve this with something called Dataloaders. But before we solve this problem, let's look at this company nested resolver as well, because the problem's not occurring here at the moment, even though we're firing separate queries. And that's because we're using Prisma and we're using something called the find unique method. Now Prisma has something built in called query batching, and it works on all of the unique methods. So find unique, or throw, meaning that when jobs is called and say this nested resolver is executed 10 times, Prisma will batch all of those requests up and then send them as a single SQL request to the database. But it only does it on the unique style queries. So if we change this over to find first instead, and then I'll just comment this out for now so we can see what's happening. Let's just return false at the moment. Now we have no logs here. I'll come back, I'll re-execute this query, and then we'll go back to our logs. And we can see that now the company query is being executed for each of the jobs being returned. So all we have to do in these instances is, if possible, switch the find first methods to unique methods. So just change this to find unique and then rerun the request again. And now we have far less queries being executed. So we have the initial request getting the user, then the request getting all the jobs. And then you'll see Prisma has generated this batched request. So it's getting the companies for all of the job IDs, and it's using an in SQL query here. So Prisma is just smart enough out of the box to be able to handle a lot of this stuff. But in some cases, it can't do that, such as in the case of isApplied, because we're doing a count query here. So in this case, we can just write our own data loader. Now, you might be sending requests to a database, you might be sending requests to a separate REST service or any kind of external service like Stripe or Notion, any kind of third-party API. In those cases, we can write data loaders to automatically batch the requests ourselves just through writing code. So what we're going to do is I'll uncomment this again, and then we're going to install a new library called Dataloader. So I say npm i Dataloader, we'll install that. And Dataloader is a really simple package that allows us to batch up requests, and we can use that to call our Dataloader within the nested resolver, which will pass a bunch of job IDs. When we have a collection of our job IDs, we'll send a single query to the database. That will then return all of our results from a single query, which we can then distribute back to our Dataloader, and then it will appear back in the resolver. So if that doesn't make sense, no worries, we're going to go and implement the Dataloader now, and then hopefully by the end it will all make sense. So first of all, on server, let's create a new folder called Dataloaders. In here, we'll create an index file, index.ts. And although in this demo, we're just going to add one data loader, I'm going to do it in a way that's going to be scalable. So when you're building apps in the future, if you add 1 or 100 data loaders, you can just do it in a really scalable way that doesn't cause problems. So first, we'll create a function called const create data loaders. And in here, we'll just return an empty object for now. And then we can export our data loader. So we'll just leave that as blank for now. And then let's go back into context, and we're going to add data loaders to context. So we'll import our create data loader method. Inside the context type, we'll say data loaders is the return type of create data loaders. And then inside our create context, we actually add the create data loader function. The reason we add it to context is because context is created every single time a request is received. And since data loaders are batching and caching up data, we really don't want to leak information between requests. If we were to create this data loader instance outside of create context, so just in the context of the application, it would mean that any request that comes in for the same data loader would continue to batch up all of the same information, meaning that data would leak between requests. So if you're using data loaders to access sensitive information like user information, if you were to initialize data loaders outside of create context, that user information could be leaked between users. So it's super important that you only initialize within the create context method. So with this in place, what we're going to do is we're going to take this query and we're going to turn it into a data loader. So we're going to optimize it to be able to access many isApplied statuses within a single query. So to do that, we'll go back into data loaders and we'll create our first data loader, and we'll call it isApplied for job data loader. Then we'll import data loader from data loader package. We'll create a function, const create is applied for job data loader, which is just going to be an arrow function, and then we'll just export this. Now we can go back into index of data loader and then apply this first data loader. So we say is applied for job is equal to create is applied for job data loader. And then we'll just import this at the top. So this is our framework to be able to add more data loaders. So in the future, if you want to add more, just add them to this same list. And again, make sure you're using like a factory function method so that we're creating the new instances of the data loader on every single request. So let's go ahead and implement the first data loader. So we'll return a new instance of data loader. And inside here, we'll have a callback. So this will get executed every time we call our data loader within our resolver. And you'll see that full setup in a second. So this is going to be an async callback. And the only thing we're going to accept is a read-only array of strings, keys. So these will be a list of all of our job IDs. For now, let's just return an empty array. Now we need to access the Prisma database and the current user in this data loader. So let's go back into index and we'll create some arguments that are going to be passed down into all of our data loaders. So I say interface data loader args, and we'll take Prisma, the Prisma client, and the user ID as well. So we'll import this, then the args we accept are going to be of this type, and then we'll pass them into our data loader as well. Let's export this so we can use it within our individual data loaders. Now let's go back into context and make sure we're passing these arguments through. So we pass in Prisma, and then we pass in the user ID as well. So now let's jump into our resolver, and then we can call this data loader directly. So let's comment this out for now. So we'll say const isApplied is equal to, and then we'll await, because this is going to be a promise, a context data loaders. So these are the data loaders we've just added to context. Then we'll say that isApplied for job data loader, and then we call .load, and this is specific to data loaders. So this is how we load data on individual data loaders, and then we'll pass in a job ID. This would get called, say 10 times, passing in a job ID for each job. Then inside data loader, we have an array of keys. So the data loader would have batched up all of those calls, and then when it's done, it returns the array of keys. We can then execute a single database query and return all of the results as an array as well, which will map them back to the particular call here, and then we'll have the correct isApplied status. So then we can just return isApplied here and then leave it at that. So we now just need to convert this into a query that can be executed as a single request. So we say const counts equals await, and then actually let's just grab our arguments here, Prisma and user ID. We'll say prisma.job.find many. So we'll fetch all of the jobs based on the provided keys. So these will be job IDs. So we say where, and we'll say ID in keys as a string. So when using TypeScript, the input for keys is always going to be read-only, but that's not compatible with Prisma. So we just need to typecast it to just string, so not the read-only version. So this will return all of the jobs based on our given keys. And then we just need to get all of the jobs. And then we also just need to filter that by the jobs the user has actually applied for. So we can say applications where some ID is equal to our user ID. So now we have all of the jobs. Since we're technically just doing a count here, let's just return only the ID to make this query a little bit lighter. So now we have all of our jobs coming back. So these will just be an array of job IDs. So just this type here. We need to map this back to the keys. So this is how data loaders can work out which data to return from each call. It's because the order of the keys being passed in is very important. So the order of the keys being passed in has to match the order of the keys being passed out. So to do that, we can just use a set and a map. So we'll say, let's create our count set equals new set. So we're just creating a set here that contains all of our job IDs, and then we can use that against our keys here to map it back to the correct value. So we can say, let's return keys.map, and you'll typically always be returning a map of keys. So we have each key, which is a job ID, and then we say count set.has the key. So count set.has will return a Boolean. So that means we're returning a Boolean true or false for each key. So for all of our keys being returned here, we'll get all of the jobs where a user has applied. We create a set from this, and then we use that to map back to the keys, which will return true or false if the user has applied for a job or not. With that in place, let's just look back at our resolvers to check that a Boolean is being returned. Okay, that's good. So let's just run the server again. And now, when the job query is executed, let's look back at all the queries that are being fired. So rather than having like 10 or 11 queries being fired, we first have the query being sent to get this current user, then the query to get the list of jobs, then that batch query to get all of the companies, and then this is where we had 10 queries before. We now have a single query being fired to fetch all of the isApplied statuses. So this here is this query being fired inside our data loader. So let's just look into this one a little bit more. I'll console log the counts here so we can see what's happening, and I'll make this larger and fire this again. So we can see in our case the user has applied for 3 jobs. So product manager, UX designer, and React developer. In our terminal, when this gets executed, we're passing in all the keys of all the jobs. So keys will be equal to like 10 jobs here. So we're saying, let's find all of the jobs, but only where the user is an applicant, which returns only 3 of the jobs. We create a unique set from those 3 jobs, and then we loop over keys to return true or false if a value exists in the set or not. So true will only be returned for these 3 IDs, and the rest of the values will return false, resulting in these 3 jobs still saying awaiting for response, and the rest not saying awaiting for response. Now, this is just something that you need to be aware of when working with GraphQL. So anytime you write a nested resolver, so not a top level resolver inside query or mutation, a nested resolver inside a particular type, you should be aware that those resolvers are being executed. So just keep that in mind every time you're writing nested resolvers and you have the ability to return a list of results. Data loaders are going to be required. And also, if you're using Prisma, then they have query batching supported as well, which means most of the time you can just rely on that if possible. We're halfway through the course now. By now, you should have a fundamental grasp of the basics of GraphQL. Next, we're going to jump into more advanced topics like testing, error handling, and microservices. So you can start to see how you can build production-ready GraphQL applications in industry. We're just going to have a little refresher on the GraphQL application that was built in the GraphQL Fundamentals part of the course. If you're jumping on directly to GraphQL Mastery, stick around for this video. We're just going to go through the basic setup of the GraphQL application. If you did come from Graph Fundamentals, then you're probably familiar with all this stuff and you can skip this video if preferred. So in GraphQL Fundamentals, we built this GraphQL application. It has a job search section where you can search for jobs. That does both local and server-side searching. We can also log in as a user or an admin on the login form at the right here. We can then apply for jobs as well. So I can apply for this job, I'll get a waiting response. We can see all of our applications in the applications menu. I can also cancel those applications. And as an admin, we can also remove and create brand new jobs. So most of the work done so far is just constructing this application, managing the GraphQL cache, and writing all of our resolvers on the back end and queries and mutations on the front end. Across the course of the GraphQL Mastery section, we're going to look at more advanced topics such as login, monitoring, error handling, subscriptions, unions, directives, a bunch of different stuff. And throughout the course, we'll be working within the source code of the GraphQL application. So let's have a quick look at the source code so far. We have both a client-side and server-side application. Inside package.json, when we run npm run start, we're using a package called concurrently to run both the client and the server at the same time. Those will run on different ports. We also have a seed script here to seed all of the data into our database, and we're just using an SQLite database, so you don't have to set up any third-party tools here. We've already configured tools like CodeGen, so you can run npm run CodeGen to generate TypeScript types based on our GraphQL types. We can also migrate the database with npm run migrate. And if we look inside the README, all of these commands are also documented here. So when you install the application, run npm install, seed the data with npm run seed, and then start the application with npm run start. When we're logging in as different users in the application, we have both a regular user configured, user@example.com, and then the admin user, admin@example.com. And both the passwords for these are password123. In the server side of the application, we have an index file which initializes our GraphQL server, which also uses Express. We then configure things like context to do authentication and authorization via cookies. And here we have access to things like Dataloaders, the current user, the login and logout methods, and access to the Prisma database as well, again connected to an SQLite database. We've also configured our schema in a scalable way. So inside entities, we have all of the different entities available, company, job, and user. These are combined into a single schema within the schema.ts file. If I look inside a single entity like job, we have all of the resolvers, including any nested resolvers, so search jobs, create job, delete job. And these are fairly simple at the moment. They take a user input, make a call to the database, and then return some data from those resolvers. We have a matching schema as well. And then within each entity, we only have resolvers and types related specifically to that entity. So for job, it's just responsible for the job types, user just for the user types, and of course company just for the company types. The front end of the application is completely written in React. We're also using Apollo Server and Apollo Client across the application, and then React Router as well. Inside client.ts, we configure our Apollo client using just the HTTP link, and then the basic in-memory cache. If we look inside routes, we have the admin route, the job board route, and the profile route. These contain queries related directly to that route, and since we're using CodeGen, when we generate types, they will be generated next to the query files themselves. So in profile, for example, I can access the use cancel application hook, which imports code from the generated queries, use cancel application mutation in this case. If we look in job board, for example, we have queries to search jobs, and then we have the generated types for this, generated with npm run CodeGen. And inside the job board, we have hooks like use search jobs, which use the generated queries, use search jobs query. Inside components and UI, we have a bunch of existing UI that was already pre-written. The point of this course is obviously to focus on GraphQL, and we're trying to get away from writing as much front-end code that's non-GraphQL related as possible. So at any point, I will provide any extra UI code for you just to copy and paste into the application, and then we can focus purely on writing the GraphQL network code and dealing with things like cache management, unit testing, and anything else like that. So that's just a quick refresher on the GraphQL application. Now let's jump into the rest of the course content. Across the next few videos, we're going to look purely at implementing all of the backend tests for our system. Now, there are many ways that we can write tests. We could, for example, call the resolver directly, because at the end of the day, these are just functions. So in our test file, we could import our resolvers, call search jobs, pass in some mock data for root, args, and context. This code would get executed, and then we could just assert the results. But the issue here is none of the nested resolvers would ever get called, and the schema itself is not tested. So there's a huge amount of coverage that we would lose if we were to just call the resolvers directly. Now, if you're working at many startups and some large enterprises as well, I've found that the best way by far to write GraphQL tests is to go down the integration / end-to-end route. So over the next few videos, we're going to be setting up our test framework, and then we'll be able to create test suites like this one here, create job.test. What we'll do is we'll be able to seed data in our database, set up a test server that we can actually execute queries against, then execute that query. So in this case, we're sending a create job mutation, passing in all the variables as well, and then we get the data and errors come back, and we can actually assert on that response. So we say we expect errors to be undefined, and we expect the response from data create job to be equal to the variables that we passed in. Now, this is as close as possible as you can get to a real production environment without actually being in production. The coverage is massive, and they're really simple to set up as well. Like, all we've done is seed some data, set up our test server, execute a request, and assert the response. We can also do things like pass in the current authenticated user, so we can test if the user is or is not authenticated, or change the user's role as well. And all we have to do at the top is clear the database before each test. No mocks are required, so we don't have to mock the database or mock context or mess around with loads of little things like that. Once the framework is actually set up, these tests are really, really easy to write. And as I said, the coverage is huge, so you can have a lot of confidence with writing fewer tests as well. You can also do things like test the relationships. So here in create job mutation, we're grabbing the relationship for company, and then inside our assertion, we're actually testing that the company has come back as well. So here we pass in the company name, test company, and we expect that a relationship has been defined for that company. So in the next few videos, we're going to create this helper, create test server, and then we're also going to configure our Jest config, so Jest backend config. And this is required because Jest by default cannot handle GraphQL files. So we just need to do a little bit of configuration there, and then the main work is going to be in create test server. So check out the next video and we'll jump straight into that. Let's just get the boring parts out of the way. We need to install a bunch of modules for our test setup. So we need Jest, TS Jest, Babel Jest, types Jest, and GraphQL tools / Jest transform, and then --merge as well. So these libraries are mainly needed just for Jest to be able to handle both TypeScript and GraphQL files. And then here --merge we'll need for our test server framework that we'll set up in just a second. So let's just install these, and through the magic of editing, they are installed. First off, let's configure Jest. We'll create a file called jest.be for backend.config.js. Let's start with this. We'll say module.exports equals an empty object to define our config. The preset we need is TS Jest, so the module we installed earlier. This will allow Jest to work with TypeScript. Then the test environment, it's going to be Node. So on the back end here, we're only working in a Node environment. Then we define a config test match. So when we run Jest, we want to target all of the files within the server directory that end in test.ts. Now with these in place, Jest can handle TypeScript files, but it cannot yet handle GraphQL files. So we need a transform config for this, using the GraphQL tools / Jest transformer that we installed just a second ago. We define a config transform. In here, we define a glob pattern for GraphQL, and we set that to use the Jest transformer. So that means anytime Jest comes across a GraphQL file, it will use this library to handle that file. Then with that transformer in place, it actually breaks TS Jest. So we need to add the transformer back in for TS Jest. So we say the glob pattern target any TS file. Then we'll say use TS Jest, and then we'll pass in the config option, isolate modules there as well. I'll zoom in on this because I know that is pretty ugly, but this is the glob pattern I'm using to target all TS files. Let's save that, and then we'll go into our package.json and we can define two new scripts. So at the moment, because we're using React testing library, the test setup is just React scripts.test, but this is actually only going to run the front end tests. So we'll just say :fe there, and then we can say test backend, then we'll run Jest, and then we'll target our backend config specifically. So we say Jest --config, so that's the config flag, jest.backend.config.js, which will target this file here. Now with this setup, we can start to execute tests. So inside server, entities, job, we'll create our first test suite here. So I'll say create job.test.ts, and we'll add our first describe block, create job, it creates a new job, and then let's just test that we can actually run our tests. npm run test backend. There we have it, the test passes. So now we need to set up our test framework, and then once we have that framework, we can implement the first test. Inside server, let's create a new folder called test utils. In here, we'll create a file test server, and this will contain the actual Apollo server we'll use to execute queries against during our integration testing. Let's import Apollo server, then the request and response objects from Express. So these are just types. Then the merge function from Lodash.merge, then our actual schema. So this is the exact same schema that's being used in our production application. Then we need create context. Again, this is the same context that's being used in our production application. And then a helper deep partial, which we have not defined yet. So let's go into types, create a new file called common, and we'll define our helper deep partial. So say export type deep partial, takes the generic t. If t extends an object, then we loop over the keys of t and then call deep partial again. Otherwise, we just return t. So let's save that. So this is just a TypeScript helper which works in the exact same way as partial, except it does it against all keys at every level. So the default partial method is shallow and does not work recursively, and we need that for our setup. So now we have all these imports in place. Let's define our create test server function. We say export const create test server will equal just an arrow function, and from here we'll return an object with one property on it, query. Query is the function that we'll call to actually execute GraphQL queries from our tests. So to do that, we need our Apollo server. We say const server equals new Apollo server. And then the only thing we need to pass in is the schema. Now inside query, we can call server dot execute operation. Now this is a method provided by Apollo specifically for running tests. Here we can pass in a query and then the variables as well. And then we can await for a response from here. So I say await, meaning this needs to be async. And then Apollo returns a response in a particular format. So we just need to say if res body.kind equals single, then let's just return res.body.single result. And otherwise, let's just throw an error because this is not the response that we would expect. Now, this is just very specific to Apollo. If you're using a different testing framework like Yoga, the setup of the server would be done in a slightly different way, but the concept is still the same. We can set up a server, send queries and variables to it, and then get a response back from that. Now, we need to also implement context into this as well, because at the moment, we're not using context. So we want to be able to test with the authenticated user and access things on context, such as the login method, the logout method, the data loaders, and be able to access Prisma from our resolvers and then access the currently authenticated user as well. And this is where we'll need both the merge and deep partial methods. So first, let's define a type that we can pass into our create server method. So we can pass in test context to be able to do things like change the currently authenticated user. We'll say interface test server args is going to equal a deep partial context, meaning that we don't have to pass in the entire context if we only want to change a small part of it. We could just pass in, say, the user, and then our test context will get merged deeply on top of the real context so that the context being passed into the resolvers is complete, except part of it contains our test data. So here we could pass in users, mocks, all sorts of things. So we have a lot of options when running tests later. So this will be optional. And then we'll say args is equal to test server args. Then in query itself, we need to accept the query and variables. So we'll say query args. Query will always be a string and variables will be a record, each key being a string or any. So we pass these across. Query args.query, query args.variables. Then above this, we can configure the context. So we say const context equals create context. In here, we need to pass the express request. For now, let's just pass an empty string and then response, just an empty string as well. We'll define these in a second. Then we define const context value, which is going to merge the context and the context we passed in. So we say equals merge context, the context we pass in from the top here. So all the values passed here will be merged on top of this. We get the context value, and then the second argument of execute operation, we can pass in the context value. Now all we need to do is define a mock query and mock response, because we're not actually working with Express here at all. We're only working with Apollo. So at the top I say const mock request, and then const mock response would also just be an empty object for now. I can pass this in as arguments here, response, and then we have the types from Express. So I'll say as request, as response. Now let's look inside context to see how we're using request and response, and then we can find out what we actually need to pass into these objects. So inside context, you can see on request, all we're accessing is cookies.token, and then on response, we're accessing the cookie and the clear cookie methods. So let's just mock these because we won't actually be handling cookies in our tests. So here I define cookies as an empty object, and here I define cookie as just a function that takes a name and value, and then just as a console log, and a similar thing for clear cookie as well. So let's just go over this file one more time. We've got all of our imports at the top. We mock the request and response because in the case of our tests, we're working directly with Apollo and not Express. We then define a type which allows us to pass a partial version of context. We then create our helper, create test server, passing in the arguments, which is going to be context. We define our Apollo server, passing in the schema. We then define a single function query, which accepts two arguments, query and variables. We then create our real context, passing in the mock request and response. We then merge our test context on top of context so we can change individual parts for each individual test. We pass that into the second argument of execute operation, and the first argument will be query and variables. We then get the response from execute operation. We check if the kind is single. Again, this is just a specific thing to Apollo. If it is, we return the single result. Otherwise, for now, let's just throw an error. And with that in place, we can now implement our first test. So let's go into entities, job, and then back into create job test. At the top, we can import our new test helper, create test server. And let's also create some helpers so we can work with the database more easily. So inside test utils, let's create a new file called database. And this is going to be a real simple one. We import our Prisma client. We export our Prisma client so we can just work with the same client on all of our tests. Then we export a helper to clear the database. So we say clear database, and then we just go over all of our models and delete them all. So we say Prisma job, delete many, Prisma company, delete many, and Prisma user, delete many. Then we can import that here as well. So we import Prisma and clear database from our test utils database. And then we can say before each test, clear the database. And now let's actually implement the test. So the first thing we want to do is seed some data. So to create a job, you need to be an admin. We'll say const user equals await, Prisma user create, and then the data I pass in will be a name, John Doe, email, test@test.com, password will just be password, and then the role in this case. Let's actually use the TypeScript types. So we say I user role, that will import from our generated resolvers dot admin in this case. So these are the resolvers that we generated on the backend with CodeGen. They include all of the enum values as well. Now we have our user configured. We'll say const test server equals create test server. And then this object here, this is the test context. So we'll say context auth. So this is going to be fully typed as well. And then we say user. And as you see, all the fields are partial. So we only need to pass in the things we actually care about. In this case, we'll say the ID is equal to our seeded user ID, and is admin is true if the users.role is equal to admin. Now with the test server configured, we can execute an actual GraphQL query. So let's say const data and errors is equal to await test server query, and then let's just leave that as an empty object. Here we can pass in our two arguments, one being the query and then the second being the variables. So in this test, we want to create a new job. So let's define a template string. I'll say mutation create job is going to take create job input. Then we'll call create job, passing across the input. And now we just need to define the fields that we want to return in this test. So in this case, I'll take the ID, the title, the description, the type. Let's go with company as well, so we can test one of the relationships. Also, depending on the IDE that you use, you can pass hash GraphQL here to get proper color coding for your GraphQL queries, so that looks a little bit nicer. Then we just need to pass in all of the variables needed to create a job. So we'll say title, description, type, company name, location, if it's remote or not, and then the salary. And then let's just import the job type from our generated resolvers. So that will come from our resolver types again. Then this will now execute an actual query against our backend, and we can just assert the response. So the first one we care about is, are the errors undefined? Which is really important. We do not expect errors to come back from this test. So we say expect errors to be undefined, and then we can do an expect on the data. So we say data.createJob to match object. The ID in this case will be any ID because we're generating a brand new job. We won't know what the ID is up front. So we now just need to assert all of the values returned here. So we say title, description, type, and then the company that was returned as well. And then we can hit save on that. And then let's run this test again. And you can see we have an error, and that's because our input is incorrect. So we actually get told from the GraphQL server what the error is. So it says bad user input, locations, variable, input of required type, createJob input was not provided. And that's because inside variables, we need to pass the object input. So I'll save that again and then run this test one more time. And then I think we just got one more error because I forgot to add an await on createContext. So createContext inside test server returns a promise. So I just need to await that. And then if we run the test one more time, this one should pass. And there you have it, the test has passed. So now we have the test framework set up. I'll just go over this test one more time. We seeded a user, we set up our test framework, we passed in the current user to context. So this was merged on top of the real context returned here. We then executed our request, passing in a GraphQL query and all of the variables. We then assert that there's no errors and then assert that the data returned is what we expect. Now with this in place, we can write a couple of more tests just to show you how easy it is. And then once you get used to it, you can really fly through these quite quickly and the friction of testing pretty much melts away. So thanks for sticking around. I know that was a long one, and I'll see you guys in the next video. Okay, let's go ahead and add one more test. So inside user, we'll write a test this time for the user entity. What we're going to do is inside schema, we have the user type, and you see we have the applied and owned jobs nested resolvers here as well. So in this test specifically, I want to test the applied jobs nested resolver. So what we'll do is we'll seed the user, have them apply for 2 jobs and check that the data coming back is in fact correct. So let's create a new test file here called applied jobs.test.ts. And here again, we'll need our test server, our database helpers, clear database and Prisma. And then we'll need 2 types as well. So imported from the generated resolver types, we'll have iJob type and iUser role. Let's define a new describe block. And here we'll give it the title user.applied jobs, and let's say it returns the jobs that the user has applied to, and this will be an async test. So we'll need to seed a user, a company, so then we can seed 2 jobs which we will have the user apply for. Then we'll define our test server, we'll run the query to get the currently authenticated user and their applied jobs, and we'll validate that all of the jobs they've applied for are returned in that list. So first we'll seed a user, so user is equal to prisma.user.create. We'll give it the name test user, the test email, test password, and this time the role is just user. We'll then define a company, which we need to attach to all of the generated jobs. So we'll just create one company here, test company. Then since we need to generate multiple jobs, let's define some common job data so we don't have to repeat ourselves. So I'll define a new variable here called const job data, and we'll give it title, description, type, the owner ID being the current user. So this won't actually be relevant, but we just need it for the test. The remote flag, the location, the salary, and then we attach the company as well, just through the company ID. Then we need to seed our 2 jobs. So the first one we'll call job 1, and we'll create a brand new job. We'll supply some data. The first thing we spread in is the common data that we defined above. We then want to attach the current user as an applicant. So we say applicants connect. So this is just specific Prisma syntax. And then we pass in the ID of our user. We can then copy and paste this for our second job as well. So job 2. Then we define our test server, just like we did in the previous test. And then we pass in the seeded user. So this user at the top as the currently authenticated user. So we just do that by adding the user to context. We then want to actually execute our query. So we say const data equals await test server.query. This time we're passing in a query rather than a mutation. So we define our type query and then we pass a template string, and again we're using hash GraphQL just to prettify the GraphQL query. Then we say query and we'll access the me query this time. So that's this query here. And then from me, we want to get the current user's ID and all of the applied jobs as well. And from the applied jobs, all we want to grab is the actual ID, just so we can validate that the correct jobs appear in the list. Then we finally just pass in empty variables. We could update the test server just to make variables optional. So for the queries that don't require any variables at all, we don't have to pass this, but that's just an improvement we can make in the future. We then just need to assert our response. So from data, we're going to get an object with me on it because that's the query that we executed. So it'll be data.me. So we say expect data.me to equal, and then we've returned here the ID and applied jobs. So we need an object with that exact shape. So we say ID should equal the currently authenticated user's ID and then applied jobs. And this array could come back in a sort of random order, depending on the order that Prisma actually inserted the entries into the database. We don't want a flaky test. So rather than just asserting an array, let's do expect array containing, which means the array could come back in any order. And then we'll pass in an array and then the first job and the second job. Obviously, you could stabilize this array by adding a created at date to the applied jobs and then ensuring that the results are returned in the order of the created at date. But in this case, we haven't done that. So I'll just use expect array containing for now. But just to note that when you are testing arrays, that's something to look out for because it can cause flaky tests. So that is the test implementation done. And we also just need to clear the database before all of our tests as well. So again, we say before each, await clear database. And now we can run our test again. And there you have it. All of the tests have passed. Okay, this time let's add one more test to user. So in our entities user, we're going to test this time the login mutation. And the reason I want to test the login mutation is because on context, we specifically call login here. So this is an interesting case to show you how you can mock certain data that you might not actually want to run inside the test. So in this case, we will execute login, but we'll replace this with a mock just to double check that it was called with all of the correct variables when we execute our mutation. So inside user, we have login. We'll pass in the email and password. We'll find the current user. We'll validate that the password actually matches. And then we call context auth login. So not only do we want to test that the correct user was returned, but we want to test that this was called with the correct data as well. So we'll add a test now, and then we'll need to set up a mock to work with this. And we can already do this with our test server setup. So inside user, let's create a new file called login.test.ts. And again, we import all of the same stuff at the top. So in this case, we want Prisma, clear database, the correct test server, and the iUser role. We'll say describe, login, and then as before, we'll say before each, and then we'll clear the database. And then we'll say it logs in the user. And this can just be, again, a regular async test. Then let's seed our user. So we say const user equals await prisma.user.create. Then we'll pass in data. And for this, we'll need the name, the email, the password, and then the role. This time will just be user. Let's create our test server again. So we say const test server equals create test server. And then for now, we'll just pass in an empty object. Then we can execute our query. So we'll say const data equals test server.query. We'll pass in a query. This time we'll be calling the login mutation. So we say mutation login, passing in the login input. We pass that across to the login mutation, and then we return just the ID of the user. We also need to pass in the variables as well. So if we look at the mutation, login input takes an email and password. So we need to pass in the input, email, and the password. So these values match the values defined in our seeded data at the top. We can then just do an expect on the data to ensure that the correct user was returned. So we say expect data.login to equal, and then we give the ID being the user ID. So if we run this test, you'll see that it passes, but we get this console log as well. So we say cookie was set. And that's because inside context here, we'll call login, but then we're calling res cookie. And then inside of our test utils, so if we go inside create test server, you see we have this mocked cookie call. So this is the log that would have been fired here. But rather than even getting to this point, we could just validate that login itself was called with the correct variables. So if we look back inside the user resolvers, we have login, and you can see we're calling const.auth.login. So let's just mock this to validate that the correct ID and is admin status was passed in. So back in our test, at the top here, we'll say const mock login will equal a Jest function. And then we can pass in a context auth login, passing across mock login. With that in place, we can then come back down to the bottom here and add another expect. So we say expect mock login to have been called with, and then the ID being the user's ID, and then is admin false because the user at the top has the role user. So I'll hit save on that, and then we can rerun this test again. And there you have it, the test is passing, so this is being validated. So obviously you could expand on that if you wanted to. You don't have to set up the test in a way where we're mocking the response exactly like this. So if you wanted to actually call this function and instead mock res cookie, we could change the test server so that we're actually passing in the mock express request and response that way. So then you could test the cookies directly if you wanted to. But this is just an example of how you can pass mocks into the create test server and then run expectations against those mocks. In the next few videos, we're going to go through and set up all of our tests for the front end of the application. So we can run Jest tests using React Testing Library. We can click around in our app. Actual GraphQL queries will be sent off and responses will come in, and then we can test how the app has responded to certain actions. Now, there are many ways you can set up tests. If you're using Apollo recommend a certain way to do it. If you use a library like Urkel, there's a different setup for it. So let's just look at some of the examples and then we'll decide on the approach that we'll actually take. So with Apollo and React, they provide this mocks provider, which is specifically designed for testing. So we'd wrap our component in mock provider and we'd supply a bunch of mocks. Those mocks would match specific queries. So when that query is fired, the mock data is returned, and then we can check that that data is rendered in our component. So in the case here, we have empty mock set up, and then we're rendering this component dog with the name book. Then further down, you can see we actually have one of the mocks added. So the request would be the get dogs query with the variables passed in name book, and then this is the data that would be returned. The issue though that I found with this kind of setup is you end up with these massive mock files because you have to supply all of the data that could be returned from the getDog query. So in this case, getDog query is requesting ID, name and breed, and we have to supply all ID, name and breed. Now that's okay for these smaller queries, but when you end up with massive queries, you end up with these huge mock files that inevitably get shared between different tests because you don't want to copy and paste a bunch of JSON mocks, which means the tests become polluted between each other. So if you have one test which needs a particular set of data and then another test is relying on those same mocks, you change the mock for one test and it breaks another test, and you just end up in this world of hell where the mocks are constantly out of sync with the actual queries and you have to constantly go back in to make sure that they're remaining in sync. Instead, what we can do is use the mock utility from GraphQL tools. What this will do, so inside our example here, what this will do is define a GraphQL schema that automatically mocks all fields requested. So here we have our schema. So the schema for the job board app, which is just the entire introspection result, including information for all of the queries and mutations. We pass that into our add mocks the schema method coming from GraphQL tools mock. And then with that, we can define a GraphQL instance, which we can pass the schema with mocks to. We can pass our query to. So in this case, we're going to query search jobs. We'll request ID, title, company name, and is applied. We pass in any variables that we want. And then I've supplied no mocks here whatsoever, but let's have a look what happens when I run this file. So you can see I've run the search jobs query and we're getting an array of 2 entries back. All of the data here has been automatically mocked. So ID is just a random UUID. Then we've got title, hello world, the company, and all of the relationships are automatically mocked. And then is applied, it's true in the first case and false in the second case. So this means that if we want to just check one particular field of a query, say we just want to test that the title is being returned and rendered okay, we don't need to supply a mock for all of the extra fields, meaning our tests can remain concise and small and very maintainable. So let's have a look at an example test that I've written using the framework that we'll develop in the next few videos. So here we have a test for the job board. We're saying show the job title in the job card. And let's just have a look a second at what this component looks like. So here we have the job board and all of the jobs are rendered. So we're just going to write a test that returns one job, and we just want to check that the title is rendered on screen. We don't care about all of the extra fields in this particular test. So we don't want to add mocks for those fields. So in our case, we use our mock server, we add the mocks for search jobs, and we return a single array with just ID and title. We then render the job board just like you would in any kind of React test, and then we can check if software engineer, so the title mocked here, is actually rendered on screen. With this in place, the GraphQL request would still fire, and it would still return mock data for all of the fields that we didn't specify. But the fields that we did specify, so title and ID, would always equal the value that we explicitly provided. If we were to follow the approach recommended by Apollo, we'd end up in a situation where we have to supply all of the extra fields that we don't actually care about for this test. So in the next video, what we'll do is we'll set up a Jest so we can actually run these GraphQL tests, and we'll create our helper, this mock server here, with all of the methods, listen, reset handlers, close, and add mocks. So add mocks is going to be the really important one. And you might be thinking, how does this actually intercept network requests? Like, are we monkey patching fetch or something like that? In fact, we're using another library called Microservices. And what this will do is, inside a node environment, which our tests will run inside of, it will intercept all network requests. So in this example provided by Microservices, any requests sent to the example.com user endpoint would be intercepted, and then this JSON payload would be returned. So we can use a combination of Microservices and the GraphQL mocking utility to automatically mock any request sent to the GraphQL endpoint. We can then merge our manual mocks with those automatic mocks to always return a complete response, no matter how big or small the query being sent, and then we can test individual fields without having to supply massive mocks. Our app is using Create React App at the moment to render the front end of our application, and then we're just rendering our own backend using a standard node server. But since we're using Microservices, the default setup provided by React scripts won't work, so we just need to configure Jest so we can start to implement Microservices with our GraphQL mock server. So if you're not using Jest and you're using a different testing framework, you could probably skip this video, but if you're following along, then please stick around because we'll need this to actually run the tests without running into any errors later on. So just as we have a custom config for the backend, we want to do the same for the front end as well. So we say jest.frontend.config.js, and here we'll say module.exports. We'll provide the preset ts.jest so we can run our Jest tests with TypeScript. We provide the test environment Jest fixed JS DOM, and this is needed for Microservices because the standard JS DOM misses a bunch of node internals to be able to actually intercept our network requests. So we'll install this module in just a second. We then test match for all of the TypeScript or TSX files within our source folder. So we say source, any file that ends in .test, .ts, or tsx. We then include the test file setup tests, which is already available within our source. The setup test was provided by Create React App, and we'll need to modify this file in just a second, but let's just include it in this test config as well. We'll save that, and then let's just install this library as well. Then inside setup tests, let's just keep this import, which provides us all of the extra testing utilities provided by a testing library. Then we need to import a couple of new things as well. So we need a new library called JSDOM testing mocks, which is needed by Tailwind to avoid some runtime errors when executing animations. So we'll install this as well. Then we'll just use this. So we're importing mock animations API from Jest on testing mocks. We'll call that. Then we need Jest use fact timers as well. And then finally, you'll sometimes get these annoying errors when you're running tests with React testing library, which will tell you not to use act in certain conditions. You've probably seen it if you've ran front-end tests a lot. But to get rid of that, we can just monkey patch the console.error. So we say const original error equals console.error. We then replace error with our own function. And then we say, if the error, so the first argument of error includes warning React DOM test utils act, then let's just return. Otherwise, let's just call the original error and passing in all of the arguments. So that just omits this particular warning, which happens during a bunch of tests, which we don't really care about. You don't have to include this, but it will make your console output a little bit tidier. With that in place, we can go back into package.json. And then here we have test front end. So we can replace this to match the same syntax as test backend, but we're going to be using our front end config. So I'll pop in the new config here. So it's exactly the same setup, Jest, and then config, and then point to our front end. Now with that in place, I can go into routes, job board, and this is where we'll add our first test. So I'll add jobboard.test.tsx actually. So in here, let's just set up a very basic test, just purely to validate that our testing framework does work. So I'll say describe job board, it passes, expect true to be true, and then just export here at the moment, so we don't run into any TypeScript errors. We can remove this once we actually start to import modules at the top, and I'll run that, and that passes. So that's the basic setup for Jest. In the next few videos, we'll set up all of the other helpers needed to run our GraphQL and React tests. Let's go ahead and add the test utility needed to run all of these mock requests inside our tests. So earlier we showed an example of the test where we mock individual queries and mutations, and we use this create mock server to achieve that. So in this video, we'll actually implement create mock server. So inside source, let's create a new folder called test utils. And inside here, we'll create a new file called mockserver.ts. Now mock server will use a combination of mock service worker and the GraphQL mocking utility to mock any request sent to the GraphQL endpoint. So first, let's export a new function called create mock server, and this is what we'll import into all of our tests. At the top as well, we'll need a bunch of imports. We'll need setup server from mock service worker, and we're using this inside the context of node, which our unit test will run inside. We'll also grab the GraphQL utility, and we'll map that to mock service worker GraphQL, and then the HTTP response from mock service worker. We'll then import add mocks the schema from GraphQL tools/mock, make executable schema from GraphQL tools/schema, and then the GraphQL build client schema and print schema packages from the GraphQL library. We'll need to install these three modules as well. So we'll do that now. So we say npmi mock service worker and then also GraphQL tools/mock. So mock service worker has this concept of handlers, and we only need one handler just because all of our GraphQL requests are sent to the same endpoint. But for now, let's just define an empty array for handlers, and we'll implement this in just a second. And then we'll define our mock service worker server using setup server. So we'll say const server equals setup server, and then we pass in the handlers. From here, we can return all of our methods. We'll return listen, which maps directly to server listen, reset handlers, again mapping to server reset handlers, close, which maps to server close, and then we'll add one more, add mocks, and this is a function we'll call to actually add the manual mocks to our mock server, but we'll just leave this blank for now because we need to create another function. So here handlers is just set to an empty array at the moment, and let's create a new utility to actually return those handlers. Const create mock handlers equals an empty function. From here we'll accept some mocks, but let's just set this to an empty object for the moment. We'll type this out in a minute as well once we've got all of our types ready. So to mock our server, we actually need an introspection result, which we haven't generated yet, but let's just assume we have it for the moment, and then we'll generate it using CodeGen in just a second. So we'll say const typedefs equals print schema. Inside print schema, we'll pass build client schema, and then inside here, we'll pass our schema JSON, which we'll import in just a second. And then let's just set that to as any at the moment. Then we'll say const schema equals make executable schema, passing in the typedefs, and then we can define our schema with mocks. So we say const schema with mocks equals add mocks to schema. Inside here, we'll pass the schema itself, and then let's add some mocks. So inside mocks, we need to mock datetime because that's a custom Scala that we set up on the server side. So for now, datetime just returns a new date and then maps that to an ISO string. And then we can spread in our manual mocks. So This means add_mocks schema will mock all fields that have not been passed in by mocks. So in our test, if we were to mock, say, the ID or title field of the job entity, those fields would always be predictable and the fields we passed in, and then everything else would be automatically mocked with this setup. Now we need to actually configure the handlers for our mock service worker instance. So we say const handlers, and that's going to equal an array, and then we'll execute this function to populate the handlers here. We only need one handler, and that's for all GraphQL operations. So we use the mock service worker GraphQL utility, so MSW GraphQL, and then we say operation. Then we give this an async callback with the arguments query and variables, and then this is just an arrow function. So anytime a request is intercepted, this callback would be executed. We'd receive the query and variables. We can pass that to our mocked GraphQL instance, then get the response from that instance and return it from this callback. So we say const data and errors, which will come from GraphQL. Here we'll pass in our schema with mocks. So that's the schema with mocks defined here. We'll then pass in the source query, then the variable values. Then we use HTTP response from mock service worker to return some JSON from this callback. So we say return HTTP response.json with any. And the reason we use any is because we don't actually know the shape of this JSON up front. Any query can come into this, so the response can take on many, many shapes. So for now, let's just add any here. We pass in an object and give it data and errors, and then we're good to go. So finally, we just return handlers here. And then instead of an empty object here, we can call create mock handlers, passing in any mocks that we need. And then again, we can define mocks here as an empty object. Then finally, inside add mocks, we can also recreate the handlers and update the server again. So here we pass in next mocks. So these will be the next set of mocks that we want to add to our server. Then we say const next handlers equals create mock handlers. So the same function we called here, passing in next mocks. Then we say server.use and then pass in those spread handlers. So this is almost the same setup as we have here, and it just basically replaces all the handlers that we originally set up. So if we want to change the mocks between tests, we would call the add mocks function. None of this is type safe at the moment, so when we're passing in mocks, we won't get any type hints, but we can achieve that through CodeGen, and we also need to generate the schema JSON from CodeGen as well. So let's jump over to CodeGen now and generate the two different files for that. So we're already generating two files for the client in CodeGen, and these are so we can have type safety for React hooks. So just above this, let's pass in a new config to introspect the schema and return it as JSON. So we'll say let's generate a file at source types schema.json, pass in an object for that, define the plugins property, and then the only plugin we need is called introspection. For this plugin, we need the package GraphQL CodeGen introspection. So let's install that, npmi GraphQL CodeGen introspection. So I'll hit save on that file, and then we can run CodeGen. And then inside source types, we'll get this schema.json file. Then in here, I can import schema.json from types, schema.json. And now we have our mock handler set up. But again, we don't have any type safety on this at all. So let's go back into CodeGen so we can generate some types so we get code hints when we pass in our mocks later. So underneath schema.json, let's generate a new file at source types, and then let's call this mockresolvers.ts. This again will just be an empty object for now. Now the plugins for this will be exactly the same as when we generated our server resolvers. So we say plugins equal TypeScript and TypeScript resolvers, but the config for this will be slightly different. So let's define the argument config and then give it a default mapper of partial t, meaning that we can pass in only partial mocks. We don't have to supply every field for our mocks. Obviously, that's the main benefit of having this mock server. We need to supply a custom resolver as well, because the default resolver generated by TypeScript resolvers is for server-side GraphQL, whereas the type signature for our mocks is going to be slightly different. So let's define an argument custom resolver function, and that will be defined at custom resolver. And then we'll have a type called mock resolver function, and we'll add this into types in just a second. And then the final one is use type imports. So that just fixes a problem inside CodeGen that when importing packages that are purely types, it will use the import type syntax. So let's save that, and then inside types, we'll create custom resolver.ts. From here, we'll export a type called mock resolver function. We'll pass in the generics tResult, tParent, tContext, targs, and these are the generics that are required by GraphQL CodeGen. I'll show you the docs for that in just a second. This will equal a function which accepts one argument using the generic targs. And then from here, we'll either return a promise of tResult or just tResult. So let's hit save on that and then run CodeGen one more time. And now we have this extra type mock resolvers. If you go to the girl.dev and look at the CodeGen docs for our TypeScript resolvers plugin, it covers the config argument custom resolver function, and it mentions that the default is a type with tparent, targs, tcontext, and then an info argument that returns a promise of tResult or just tResult. You can provide a custom resolver function instead of the default. It has to be the type that uses the generics tResult, tparent, tcontext, targs. So that's why we have this shape here, even though we're not using tparent or tcontext. But with that file generated, let's go back inside test utils mock server. And from here, we can import query resolvers and mutation resolvers from mock resolvers. Now let's define an interface, call it iMockServer mocks, which will take query and mutation, both as optional fields, passing those types across, and then we can use that here, and again, then inside create mock server, and again inside add mocks as well. So with that in place, we now have a mock server with full type safety. So that means inside my test, I can say const mock server equals create mock server, and then I could call mock server dot add mocks, and now this is fully type safe. So I could say query, I could mock even me, or say search jobs in this case. Then in this case, search jobs requires an array, and then all of the return values are also typed. So I could pass ID, needs to be a string, say title, which needs to be a string as well, and then what about is applied, that needs to be a boolean. If I pass anything else, we'll get an error here telling us that the return type is incorrect. So this means if your data types change on your server, all you need to do is regenerate your types with CodeGen, and then anytime you have any issues, they'll pop up in your tests, which completely eliminates the risk of tests becoming stale, meaning you're far less likely to run into production issues with this kind of setup. And we're back for another video. Now, before we actually go and write the test, we need one more thing, and that's the ability to render React components. Now, we could import render directly from testing library, but we also need to set up all of our providers. So we want to be able to do things like import, say, just the job board and render it on screen without having to reconfigure all of the providers at the root of our application. So we'll set up a test renderer with all of the providers set up, including Apollo provider, and we'll also need to reset the cache between each test to ensure that there's no cross-test pollution going on. So back inside test utils, let's just create an index.ts file. Inside here, we'll import Apollo provider from Apollo client. We'll import the render method from testing library React, and we'll just call that test render. We'll import the auth provider so we can access the authenticated user inside our tests. And then we'll also import our Apollo client, which is used in our real application. And this means that we have a very realistic test setup, which is as close to production as possible. If you try and mock a lot of this stuff out, then the version of the code you're testing is not so similar to the version of the code running for real users. So the point of all these things is that we're trying to get as close as possible to the experience of a real user, but also by maintaining good developer experience. Now from here, let's export a new function called render, and we're just going to wrap test render. So we'll define a function here. We'll pass in one argument, which is the UI we actually want to render. The type of that is a React element. We'll return test render. So again, we're just wrapping the render method from testing library. We'll pass in UI, and then the second argument is going to be something called wrapper. So this is what will wrap around anything that we pass into UI. So let's define a function here called wrapper. So we say const wrapper. We'll take one argument, which is children of type React Node. We'll then clear the client cache between each test. So every time wrapper is executed, the cache will be reset. We'll then return from this a React component, which is going to match the same format as our root app. So we'll pass in the Apollo provider, passing in the client. We'll then pass in the auth provider, and then we'll finally render children. I've just realized as well, we need this to be a TSX file. That's why we're getting these type errors at the moment. Now with all of this in place, we're pretty much good to go to write our first test. So in the next video, we'll write 2 tests for job board, implementing the new mock server, which we just created, and then also the test renderer as well. Inside jobboard.test.tsx, which is inside jobboard root source, we'll now implement our first test. So let's delete this example code here, but we'll keep this import for creating our mock server. Inside the describe block, we always need to run these 3 commands. So before all, we will start the mock server.listen. After each test, we'll reset the handlers. So we say mock server.reset handlers. And then after all of the tests, we'll close the mock server, and we use mock server.close for that. Now, our first test will test that the job search section is rendering the correct title. So let's call the test show the job title in the job card. And here we can add our first mock. So we say mock server.add mocks. We'll mock a query. We'll mock the search jobs query and return a single entry, which will have ID 1 and then title of software engineer. We'll then render the actual job board. So let's import job board and then import render as well, coming from test utils. So this is the render that we've wrapped in this file here. We then just need to expect that this mock data has appeared inside the job board component. So inside job board, we're executing this hook use search jobs, which will return a bunch of results and render them on screen in these job cards. So once the query has executed and returned data, the title will be rendered on screen. And then we can use React Testing Library to assert that that value actually does exist in the document. So we'll say await for, importing from Testing Library React. And then we'll say expect screen.getByText software engineer to be in document. Screen also comes from React Testing Library. And then we need to make this test async as well, since we have an await here. Now we have these imports as well, we can remove this export. Now with that in place, let's run the test to see if it works. npm run test frontend, and there we have a test passing, which means everything is set up correctly. So let's just run the app one more time to see what we've actually tested here. npm run start. So here we have the job search section. We will render a single card. In our case, we're rendering software engineer rather than test job. So we're asserting that after the query is executed, this card has rendered on screen, and then we're just testing that the job title itself has rendered correctly. So the reason that we needed to do wait for in this case is because these are async operations. So inside job board, when a GraphQL request is executed, that request will go to the server. The server then needs to respond, and only once the server has responded will the React component re-render and then render software engineer on screen. So if we were to just do screen.getByText without wait for, it would happen too quickly and then the test would fail because we need a couple of render cycles before that data actually becomes available. So we wrap it in a wait for, which will rerun the code several times until the test passes. I think it waits like 3 to 5 seconds, something like that. And then when it finally sees software engineer, the expect passes, and so the test passes as well. Let's now add a test which validates a mutation as well. So underneath here, we'll say it applies for a job. And then let's create a Jest mock here so we can validate that the data sent to the server is what we expect. So we say const apply for job mock equals Jest function. And again, let's define our mocks. So we say mock server.add mocks. First, we'll mock a query. So again, we need to mock search jobs. So we say search jobs, let's return ID 1, title software engineer again. But this time, we have to say is applied false so we can actually apply for the job, because the apply button won't be available if is applied is true. Then we can mock a mutation. So we mock the applied for job mutation. We return true from this. And then we also add in our apply for job mock, passing across the arguments. So that means once this mutation has been executed, we call apply for job mock, and then we can assert that this was called with the correct arguments. We then render the job board just like before. Then again, let's await for the software engineer title to appear on screen before we proceed with the test. Then we can start clicking some buttons as well. We're testing that when we click the apply button, the modal appears, and then we click apply again, which will send off a mutation. So let's just do that again with the network inspector open. So I'll click apply again. We send off the apply for job mutation, and then we get a waiting response appearing inside the UI. So that's the steps we need to follow for this test. So first, we need to grab the apply button. So we say screen.findByText apply. We then fire an event, fire event.click apply button. We then need to click the apply button inside the modal. So we say dialog equals screen.findByRole dialog. So when we open the dialog, this will have the role dialog. We then find the apply button within the modal. So we say within dialog, getByText apply. Then we fire a click event on the apply button within the modal. Then finally, we wait for the apply for job mock mutation to have been called. So we say expect apply for job mock to have been called with, then the input we expect. So in this case, it's input with the ID 1 coming from this job here that we would have applied for. And then we can also test that the UI is updated as well. So we can say await for expect screen.getBytext awaiting response to being document. So we're just double checking that the awaiting response information has appeared, which means that the GraphQL cache updates would have executed fine as well. So let's just import these modules, import fire event and import within. Those are both coming from testing library as well. Let's hit save on that, and then we can run these tests. And there you go, we have both tests now passing. So that's the test for show the job title in the job card and then applies for job. So a lot of this stuff here is just clicking around, and this is just standard React stuff that you need for pretty much any network implementation. But the most important part is that we've mocked our mutations, our queries with minimal data, despite our search jobs query actually requesting all of this information. All we've mocked is ID and title, then all of this information will be automatically mocked, meaning if this query changes in the future, we don't have to go back and then change our tests for fields that we don't care about in the context of that test. Now let's jump over to a new data type that we haven't looked at yet called unions. And the main benefit of a union in GraphQL is it allows a single field to return one of several different object types. It enables more flexibility in representing and querying data. And this is particularly useful when the exact type of the return data isn't known in advance, or when you want to group related but distinct types together under a single field. So let's look at our example here. We have article, video, and image. And imagine we want to run a single search query which allows us to return either article, video, or image based on the search query we provide. When we run the search, we won't know upfront which of these data types needs to be returned. So instead, we can create a union type which can equal any of these three, and we can return that union instead of these three individually. So let's first define a search query. We'll say type query, and let's call it search, and we'll take a single query argument. We'll say query, and we require a string for this. And let's say we require article, video, or image. Now this is not valid GraphQL syntax. We can't just use the or syntax directly in the return type of a query, but we can apply this to a union. So at the top of the file here, we say the union keyword that will equal search results, which can equal either article, video, or image. We can then apply the union down the bottom here. So I'll pop search result in to the array. And here I've also added the exclamation marks to say that this data type is required, but this doesn't have to be the case. You could remove the exclamation marks like so. And that is just a very brief introduction into unions. In the next video, we'll actually implement a union into our GraphQL application, and I'll show you how to query unions on the front end as well. Now, the way we're going to implement unions into our GraphQL application is on the job search section. So here we have each of the job cards, and we have some jobs that are available in just the US, and then some jobs down here which are available in the UK. Now, the address format between US and UK is completely different. So if I hover over a UK address, we would get line 1, line 2, city, and postcode. And if I hover over a US address, we would get street, city, state, and zip. Now, rather than returning two separate address fields from our GraphQL API, we can have a single address field that is in the format of a UK address or a US address. This is the perfect use case for unions. So in this video, we'll implement all of the backend for unions, and then I'll show you how to write a front-end query to request all of the information for this union. We'll skip actually implementing any of the UI work because that's just React and CSS stuff, which is kind of irrelevant for the purpose of this course. So let's just jump into the code now, and we'll implement the backend section for this address union. So inside our server entities, at the moment we have company, job, and user. And let's stick to the same pattern of having each entity under a separate folder. So we'll add a new entity folder here called address, and we'll follow the exact same format as the other entities. So we'll say index.ts, we'll have resolvers.ts, and we'll also have a schema.graphql. The index file will just copy the same format as the other index files. So let's copy this file from company and paste it into address, and then inside schema, let's define our address union. So our first type of address is a US address, and this could have a street, a city, a state, or a zip. And then we can have the type UK address, which has address line 1, address line 2, city, or postcode. We can then define the union with the union keyword, union address equals US address or UK address, and then hit save on that. Now this is the only setup we need for the schema. So it means address could be in the format of US address or it could be in the format of UK address. Now we just need to define the resolvers to work out which type of address to return for which job. So first let's just import the types. So we import type iResolvers from types resolver types, which is just the same as we have done for other resolvers. In fact, let's just copy this empty company resolver. We'll just paste that in for now, and let's just leave this empty so we can first go ahead and run code gen so we get these address types appearing in our TypeScript types. So if we launch a new terminal and run npm run code gen, we'll now have access to the address field. Now, the first thing we need to compute which type of union we've returned is a resolver called resolve type. So we say __ resolve type. We'll get an object back, and then we just need to return the string US address or UK address. Now let's look at our schema again and see how we can decide if we've got a US address or UK address. So we know that only the US address has a zip, the UK address does not have a zip. So we can say if the address that we have has a zip, then let's return the string US address. Otherwise, let's return the string UK address. So obj here would be either a UK address or a US address. So we can say return if the object has own property zip, we'll return the string US address, otherwise return UK address. So we're going to jump over to job now, where we'll actually relate the address entity to a single job. So inside schema again, inside job, we'll add a new field called office address, and this will be of type address. Let's just make it optional because in the case of remote jobs, there won't be an office address. So this can just be an optional field. Then inside the job resolvers, we need to define a new nested resolver for the office address. So we already have two set up for company and is applied. So let's first run code gen again. Now we've updated our schema, and now we'll be able to type office address and get code hints for that as well. So let's define an empty function for now. And then from here, we'll get a job come back. So job will be typed already based on our code gen types. And the first thing we need to say is if the job is remote, there won't be an office address. So if job.remote, let's return null. Now we need to return either the UK address or the office address. Now let's do this based on the other common field, location. So we'll say if location contains the string UK, we'll return a UK address, otherwise we'll return a US address, because we already have a location field here, which will just be a single string like New York, New York, or down the bottom here, London, UK. So let's say return job.location.includes UK, will return the UK address, or will return a US address. For now, let's just return dummy data from here, just so we can focus purely on the GraphQL part. So for the case of the UK address, we'll return address line 1, address line 2, city, and postcode. For the case of the US address, let's return street, city, state, or zip. In reality, you would grab this data from another data source, such as the database, but in our case, we can see just with this dummy data how unions can work. So the final thing we have to do before we run the server is add this new address entity to our schema. So inside schema.ts down the bottom here, let's copy this import for company, and we'll change the fields for address, and then implement them down here as well. So we've added address, type defs, and address resolvers to our type defs array and to our resolvers array. With that in place, let's run the server and then look directly at the GraphQL playground. So here I've already written out a search jobs query. We have query search jobs taking the search jobs input, and we're just passing that across to the search jobs query. And then the input down here, we're just passing in an empty string. All we request at the moment is an ID. So if I run this, we just get a bunch of IDs coming back. I could also request the title, and we get all the titles. And now I can also request the office address. So if I type office address, I'm getting type hints for this. But you'll notice there's nothing available if I try and request any field directly inside office address. That's because office address is now a union type, and to access fields of a union type, we need to use a special syntax. So we say triple dot on UK address, and then now inside here, we have access to all the UK address fields. So address line 1, address line 2, city, and postcode. Let me just add location here as well. And you'll notice for all of the US addresses, office address is an empty object. And we don't actually have a UK address in here at the moment, so let's just add one to our seeded data. So if I go into the code, back to seed, all of the jobs that are seeded as part of the seed scripts are listed here. So let's just look at this top one, senior software engineer. Let's change this to include the string UK, and I'll just change this to London. We'll run seed and then start our server again. Now in here at the top, we have the London address and we have the office address for that location being returned. And then for all of the US addresses, we still have an empty object because we need to also define that on the union type. So here I'll say again, ... on US address, and we'll get type hints for this. Now we can access all of the US address fields. So I can grab street, city, state, and also zip. Now let's execute this again. And now we have all of the US address fields coming back. So this is just the dummy data we defined in our resolvers. But for any UK location, we'll get the UK dummy office address. And for any US location, we'll get the US dummy office address. So this is the exact same syntax that you would also apply in your application code as well. So we can just copy this code, office address, go back into our source code. Then let's go to the front end code. So inside source, we'll look at routes, job board, queries, and here we have the search jobs query. Here we can just paste in the office address code. Then again, we can rerun code gen. And now inside job board, we have this use search jobs query and we have the results coming back. If I hover over results, the TypeScript types now look like this. So we have all of the fields that we already have, ID, title, company. Now we have office address as well. And in TypeScript, unions will use the pipe operator. So office address could be the UK address or the US address or null. So with that in place, we can then just work with this like it's standard JSON. We can look at the types. We say if the office address has address line 1 or the type name UK address, we know it's a UK address. Otherwise, it's a US address. Otherwise, it's not. Now, you can obviously implement these data types in any way you see fit. For example, using the tooltip UI that I demonstrated at the start. But that is unions in a nutshell. Okay, in the next couple of videos, we're going to look at directives. Now, GraphQL directives are a way of applying information or functionality to a GraphQL schema, but from the perspective of the schema. So it's a schema-first approach. Now, there are some built-in directives already, depending on the server that you're using. So in the case of Apollo, we have a built-in directive here called deprecated, and this would allow us to mark fields as deprecated directly from the schema. So when we run introspection and generate TypeScript types, or if we're just using the playground provided by Apollo, that deprecation information would be sent back to the client, and then we could be presented with that. So if I look inside our schema, we have the job type here, and I've already applied the deprecated directive to location. So we define this with the @ character, then we say deprecated, and then you can pass in whichever arguments are defined for that particular directive. So in the case of deprecated, we can pass in a reason, use office address instead. So if I look over at the playground now, you can see that when we're requesting a job, the location field is marked with a yellow squiggly line. If I hover over this, we get that information back. The field job.location is deprecated, use office address instead. So with directives, it's a really nice way to work to keep things in the schema and keep things all in one place. If I jump back over to the code here and scroll down, we have this other directive here as well called auth. And what this will do is prevent access to the create job mutation unless the currently authenticated user is an admin. So we say @auth roles admin. Now this is not built in. So what we're going to do in the next video is define a custom directive called auth that reads from the context, so grabs the currently authenticated user from the cookie, then validates if they're an admin or not based on the role specified within our custom directive. So let's jump over to the next video and begin the implementation of our custom auth directive. Now also in the Apollo docs, they specifically mention that Apollo server does not provide built-in support for custom directives that transform the schema. So that means if we want to implement our own custom directive, we have to use different tools. Apollo doesn't provide anything out of the box. But luckily, there are a bunch of packages already available, mainly provided by the Guild, that can help us define a bunch of custom directives. So GraphQL Tools, this package provided by the Guild, will allow us to define our custom directives, including the part we need for the schema, and then the actual JavaScript or TypeScript code we need for the business logic of the directive. So let's jump back over to our code. Now I'll leave @auth on create job at the moment, but obviously this wouldn't do anything at the moment. In fact, it would cause an error because this is not defined anywhere. But let's just hit save on that for now. Then inside server, let's create a new folder called directives. We'll follow a very similar pattern as we did with entities here. So we'll have separate folders for each directive. Our first one in this case will be auth. So let's create a folder auth. Then inside here, let's have a common index file where we'll export any of the public functionality. We'll then create a file called directive.ts and also schema.graphql. Inside index, we'll import the directive, we'll import the type defs, and then we'll just export those two as well. This is showing an error because we haven't defined anything for either of those two fields. So I'll just close this for now. Then inside schema.graphql, we'll actually define the new directive. And to do that, we use the directive keyword. So we say directive @auth will take a role. That will be of type user role, and that's a required field. And then we say on field definition. And if we look back at job, create job is a field of mutation. So it means that we can now apply this directive to any field. So it could be here at create job, here for delete job, for example, or any field of any of our custom types as well. So type query and type mutation are built into GraphQL, but we've defined custom types like here, type job. If you wanted to protect a single field, for example, title, I could put @auth roles admin next to title. And that means when we try and query for a job, if you try to request the title and you're not an admin, we would see an error. But let's just remove this for now. Now we'll jump over to directive.ts, and this is going to be a fairly complex one. So we need to implement the actual logic for our directive. And to do that, we need a few imports. So the first one is a bunch of tools from GraphQL tools/utils. We need map schema, get directive, and mapper kind. This is just a type. Then from GraphQL, we need default field resolver and GraphQL schema. Then we also need to import our context type as well. So this is the same type applied to our server context, containing Prisma, auth, and Dataloaders, specifically because we want access to the currently authenticated user. We then import the generated iUser role from our codegen, and then let's define a function called auth directive, which takes one argument, the GraphQL schema. Now, the reason we accept the GraphQL schema is because directives actually wrap the entire schema, which means every time we create a new directive, we pass the entire schema in. That will return a version of the schema with the directive functionality added to it, and then we would pass that schema into our Apollo server. So let's just export this file at the bottom. Then from here, we say return map schema, again passing the schema across, and then for the second argument we define an object. Now, depending on the different keys we define here, when our schema is actually executed by GraphQL, it will look over all of the fields and then decide whether to actually execute the field or not. So in our case, for our auth directive, we've said field definition, and the corresponding key for that on the TypeScript side is mapperKind.object field. We return a function. Then what this will do is loop over every field in the schema when the schema is executed, and then provide a field config, and then we can look for our particular directive within that field config. So first, let's try and find our auth directive. So we say const auth directive equals get directive. We pass in the schema, the field config, so the object field, then the actual directive we're looking for, in this case auth. Then this will return an array, and we just want to grab the first element of that array. So we say question mark dot and then the first index. Now we only want to proceed if we've actually found our auth directive. So I'll say if auth directive, and then we'll add a bunch of logic here. Otherwise, let's just return the field config as is. Now the first thing we want to do is grab the actual resolver for our particular field. So we say const resolve, and let's set this to a variable default field resolver equals field config. So if we look inside resolvers, we can set up nested resolvers for individual fields. Now that's kind of similar to what we're looking for here. Although we haven't explicitly defined a resolver for a particular field, GraphQL would still treat every single field as if it has a matching resolver. Those resolvers are just defined internally. So in our case, what we're doing here is inside the job schema, we'd be looking at mutation, and we'd be looping over every single field. So create job, delete job, apply for job, cancel application. And we're seeing which one of those has the auth directive applied to it. So in the case of create job, that would be picked up here. So this would get called for every single field. We'd eventually get to the field for create job. Then we'd grab the resolver for create job, since it has a matching auth directive on it. And then we can do the rest of our logic underneath. So all we need to do now is define a custom resolver for our directive, check if the user is authenticated. If they're not, throw an error. Otherwise, pass on to the next resolver in the chain. So first, let's grab the role argument from the directive. So we say auth directive.role as iUser role. So this would grab the value of the field here. In fact, let's just set this to role and remove the array syntax. So now let's override the field config resolver. So we say field config.resolve is equal to a new async function, which returns source, args, context, and info. The type of context in this case would be equal to our context. So we pass in context here, then I'll hit save on that. Now we can grab our current user from context. So I'll say const user equals context.auth.user. Then the first thing we do is just check if the user is authenticated. So I'll say we don't have a user, then just throw the not authenticated error. Then we check if the user is an admin. So I'll say if the required role, so if this role in the directive is set to admin and the user is not an admin, then we throw the error saying you're not authorized, admin access required. If we get past all of these checks, then we can just call the default resolver from field config. So the value that we grabbed before we overwrote the function, we can just call that, pass in across source, args, context, and info, and then the GraphQL server, so the Apollo server, will just handle the rest. Now we need to head into Schema. So Schema is where we've combined all of our different resolvers from all of our entities, and this is when we need to wrap the schema in our custom directive as well. So below where we've imported all of our entities, let's import the auth directive type defs and the auth directive from directive/auth. Then underneath our schema here, we now need to wrap this schema inside the auth directive. So the first thing we do is pass our type defs onto the type defs array. So auth directive type defs. Then rather than exporting the schema, we'll wrap the schema with directives in auth directive, passing the schema in, and then we export schema with directives. Now with that in place, I can just start the server again, then just double check that we're logged in the actual application. In this case, I'm logged in as the test user. Then inside Apollo server, if I try to create a job with that user, so a user that's not an admin, I'll get the error, not authorized, admin access required. And that's the error that we defined inside our directive. Meaning, we can now go into resolvers and remove the authorization logic specified directly in the resolver. So depending on the workflow that you like, you can do authorization in the resolver code, or now just apply a simple directive inside the schema, which in many ways is much more readable because all of your sort of logic is in one place. Obviously, it depends on the way you like to work and the way you like to set up your servers. But since we have both, we only need one. So I'll delete this code here. And with the directive in place, we can be rest assured that the create job endpoint is still safe and secure. So that's just a quick demonstration of implementing a custom directive. As you can see, directives can be used for both manipulating the data that's returned from your GraphQL schema to doing things like authorization checks for requests coming into your server. There are also many directives already built on NPM. So if you're after a certain kind of functionality, just Google the functionality plus the word directive, and you might find a package that's already been built. I could literally film 10 more videos on just directives alone, but that at least covers the basics and sets you up with the ability to write your own directives if you'd like to. Up until now, all we've looked at is queries and mutations, but there's a third GraphQL type that's built in, and that is subscriptions. So over the next few videos, we're going to take a deep dive into GraphQL subscriptions, what they are, how to use them, and actually implement a GraphQL subscription feature into the GraphHire application. GraphQL subscriptions are specified with the subscription keyword in a very similar way to how you'd implement queries or mutations. So you'd use the subscription keyword, give the subscription a type, and then specify which query you'd want to subscribe to. Unlike queries and mutations, which are stateless and more about two-way communication, i.e. we send a request to the server and get a response back, subscriptions are purely a server-to-client communication protocol, meaning the server would push information directly to the client, and subscriptions don't include any method to send data from the client back to the server. So let's have a quick look at an example server which uses subscriptions. So on the left-hand panel here, we have a mutation, create comment on post. And on the right-hand side here, we have a subscription, comment added. If I hit play here, we'll subscribe to this subscription. Then anytime a comment is added, instantly that comment will appear on the right-hand side. So you see I've just added a comment and it has ID 6. So ID 6 is what was returned from the mutation. And if I hit play again, you'll see on the right, the ID automatically increments without me having to go back and hit play or anything like that. That's because the server is now automatically pushing information to this client. Now the actual transfer protocol isn't part of the GraphQL spec at all. So if the information is pushed over WebSockets, server-side events, long polling, that is completely up to the library maintainer or up to us. In fact, on the documentation, they even mention this. GraphQL doesn't specify what transport protocol to use, so it's up to the server to decide. In practice, you will often see them implemented with WebSockets or server-sent events. So let's jump back over to our example here and look at the network tab to see what's actually happening under the hood. So when I hit play here, a new request appears, which is a subscription. If I click into this, we'll see that the accept type is text event stream, and we also have access to this event stream tab. This means the protocol being used is server sent events. So if I come back over to this screen and press play to create a new comment, we have a new event streaming in. And if I press play a few more times, you can see more and more events are coming back into this. Now this is a very, very simple implementation using GraphQL Yoga. So if we jump over to the code, the first thing we have set up is this pub sub, which is coming from the package GraphQL subscriptions. Now you can use any publish subscribe package, but there's a really handy one from GraphQL subscriptions, and you could plug it into Redis or just have it in memory like it is at the moment. Obviously, if you're using an in-memory pub sub, then it would only work on one server. If you're launching multiple servers, you need to use something like Redis, so you have a single central place where all messages are sent to. Now, how this would work is, in the create comment on post mutation, we create a comment just with dummy data, and then we call pubsub.publish, and then give it a name, comment added. Then we push the new comment under the payload, comment added. Then we've set up a subscription here for the same subscription type, comment added. Then we specify a callback under subscribe, and then call pubsub async iterable iterator, and then pass the same string in, comment added. That means this will now listen to and push events for any message on this particular channel, comment added. Inside Schema, we have our standard mutation, create comment on post, and then we have this new subscription, comment added, which will return a comment. So the fact that this says comment added here is the reason in the resolver why the object pushed needs to have the key comment added as well. Now GraphQL Yoga by default uses server sent events, but we're in the next video going to implement an actual subscription feature with Apollo, and their recommendation is to use WebSockets. So stick around, in the next video we'll implement a real subscription feature with Apollo server. We're going to go ahead and implement a subscription-based feature into the GraphQL application. So I've got the application open here on the right and the Apollo server open here on the left, and subscriptions are already set up within the application. If I hit create job, a notification instantly appears on the right-hand side to inform the user that a new job has been created. And if I hit job a bunch more times, you'll see that number automatically goes up. That's because this application now has a subscription set up which is listening to the creation of new jobs. If I click into this, you can see all the jobs that I just created. So I just hit create on software engineer a bunch of times. That's why that's repeated. But if I was to, change this, hit it again, you can see instantly the new job appears. So we're going to jump over to the source code for GraphHire and then implement both the server side and the client side for this feature. Now, you don't have to add any of the UI. In fact, the majority of the UI code is available just underneath this video in the course. So just grab the UI code from underneath the video and paste it into the app so you don't have to write any UI code yourself. So jumping over to the source code, the first thing we'll start with is the job entity. So because we're creating jobs and listening to the creation of a job, this subscription is going to sit inside schema.graphql inside server entities job. Here we already have queries and mutations set up, so let's add the new type for subscription. We say type subscription, and we'll call this one job created, and it will return a job. So the job type is already defined above. And we're just going to return this entire type every time a new job is created. We already have the mutation for create job, so there's nothing more to do here. Now let's jump over to our resolvers, and inside create job, what we'll need to do is, once the job has been created, we'll publish that to our pub/sub subscription, and then we'll create a new resolver for subscription to push that information to the client. But before we can do that, we need to actually set up our pub/sub client. So let's jump over to context.ts inside server, and now we'll import a new package, pub/sub from GraphQL subscriptions. So we also need to install this package. So I'll open a new terminal, npm GraphQL subscriptions. Now let's set up this pub/sub. Let's say const pub/sub equals new pub/sub. Now if we want type safety for this, we can actually specify all of the events that can be published and subscribed to. So we pass in a generic here. Let's pass in an object. The event will be job created, and the payload sent for this will again be job created, camel case, and we'll return a job. We'll then just import the job from the Prisma client. Then down here in the context types, we need to include pub/sub. So we say pub/sub is going to be type of pub/sub. So this is going to be the version of pub/sub with our generic passed in. Then down the bottom here, we can just return pub/sub as well. Then in our resolver, we can now use that within context. So after the job has been created, we'll call context.pub/sub.publish. Then we'll pass in job created. So we're getting type hints for this already. Then we pass through the object, job created, and then that will just be the job itself. So this job here. Now there's nothing more to do on this side. Now since we've updated the schema as well with the subscription type, we just need to run code gen one more time so we can get type hints when typing out the resolver for that subscription. npm run code gen. Now we've got query mutation. Above this, let's specify subscription, job created. Subscribe will be the only function we can provide. We'll have access to all the same things here as well as a standard resolver, root, args, context. Then simply we say return context.pub/sub dot async iterable iterator. It's a little bit of a mouthful. Then we pass in the same string job created. Now this will just automatically push information to our client every time we call publish for the same string. So job created in the publish method, and then job created again in the async iterable iterator method. So that's pretty much all the setup we need for the resolvers and the schema. But Apollo doesn't support subscriptions out of the box, so we need to configure Apollo in the index file to support subscriptions over WebSockets. At the moment, all we have is a standard Express server, so just a standard HTTP server, which has no configuration at all for WebSockets. So here we're going to update index to support both the standard Express server for queries and mutations, and then a WebSocket server specifically for the subscriptions. So let's import a few more packages. We need WebSocket server from the WS package, use server from GraphQL WebSocket, and that'll come from GraphQL WS lib use WS, then HTTP, which is just a built-in node module. Then let's also install these modules, npmi GraphQL WS and WS. So the main difference that we need to implement here is, at the moment, we're calling listen on app. So this is going to only listen on the HTTP Express server, whereas we need to configure both WebSockets and HTTP and then listen on both protocols. Now we have our Express app already set up. We'll define a new HTTP server, const HTTP server equals http.createServer, and then we pass the app in. Then we can define a WebSocket server as well. Const WebSocket server equals new WebSocket server. We'll pass in an object. The first argument will be server, which is equal to our HTTP server here. Then we'll define the path, GraphQL, so that's matching the same path that our Express server uses. But obviously, Express will be on the HTTP protocol and WebSockets will be on the WS protocol. Then we already have our Apollo server set up, so there's nothing else to do there. Finally, we need to call use server from the GraphQL WS package, use server, then we pass in an object. The first argument will just be the GraphQL schema, then a callback for context, and this is so our subscription resolvers have access to context. So from here, we simply return create context in the same way that we would have here. The only difference is, here we're passing in the request and response objects from Express, but those aren't available within the context of WebSockets. So inside create context, we need to make this optional. So let's change this to CTX ? And we'll say CTX here, and then CTX again down here, and then finally in logout. We've also just got a stupid ESLint error here, just saying React hooks use server cannot be called at the top level. Obviously, we're not in the context of React here, so that is not a problem whatsoever. So at the top, let's just disable that error. We say ESLint disable React hooks, rules of hooks. Then finally, we need to pass WebSocket server into useServer, and that will be the second argument. With all of that set up, we need to then come down to the bottom here, and then rather than listening on app, we can listen on the HTTP server. So let's just switch this out, HTTP server, and then also provide a console log for the WebSocket server as well. So we say console.log WebSocket server is running on the WS localhost 4000, and then at the same endpoint here as well. Now with all of that set up, subscriptions should be working on the server side. So let's jump over to Apollo Playground and then test if it's working. On the first tab here, I already have a mutation set up to create a job. So we're passing in title, company name, description, location, remote salary type, and then just returning the ID. On the second tab here, I have a subscription set up. Let's give this a name, job created. Now we can subscribe to this subscription. So I'll press play here. Then now that is just listening permanently. Then I can jump back over to create job and then just create a bunch of jobs. And you'll see them being received by the subscription. Now that means the server-side setup is complete. So let's jump over to the client and then update our client to be able to receive these subscriptions as well. Now let's minimize server, and then we're going to be working on the client side only. Inside source, we have this file client.ts, and at the moment it's only configured to work over HTTP via the HTTP link. Now we need queries and mutations to continue to work over HTTP and subscriptions to work over WebSockets. And since Apollo provides no functionality for subscriptions out of the box, we need to manage this ourselves with a bunch of different packages. First, we need a package called split, which comes from Apollo client. Then we need GraphQL WebSocket link from Apollo client link subscriptions. We need create client from GraphQL WebSockets. Then just a helper, get main definition from Apollo client utilities. So what we're going to do is continue to supply the HTTP link, also create a WebSocket link, and then use this helper split to determine which link to use depending on the type of operation being executed. Let's first define the WebSocket link. Const WebSocket equals new GraphQL WebSocket link. In here, we'll pass create client coming from GraphQL WebSocket. The only argument we need for this is URL, which will equal our WebSocket endpoint. So it's going to be the same as a standard endpoint, but we're going to use the WebSocket protocol. So we say WebSocket : / localhost 4000 / GraphQL. Now underneath this, we can define the split link. Split link works by taking three arguments. First, a callback, which receives a query, and in that callback, we can determine the type of operation. If it returns true, split will return the second argument. If it returns false, split will return the third argument. So let's first provide our callback, which accepts query. Const definition equals get main definition from that query. So the helper we imported at the top here. We can then return true or false from this. So we'll say return if definition.kind equals operation definition and the definition.operation is equal to subscription, then the second argument is the WebSocket link. Otherwise, it's the HTTP link. Then rather than supplying HTTP link to the Apollo client, we simply just supply split link. Now that's set up, we should be able to receive WebSockets from the server. So let's jump over to containers inside source and then configure the actual notification service for when a new job is created. Let's create a new folder called job created notification. In here, we'll just have an index.ts where the actual React code will sit. Then we'll have queries.graphql. Inside here, we can actually define our subscription. We say subscription, job created, then return an object here. Then we're going to call it the job created subscription. So this is just the named type of the subscription on the client side. This is the actual subscription that we're calling. Since this returns a job, we'll be able to get ID and title from that job. We can then run codegen again. which will generate a fully typed subscription hook for us to use in our application. So here we have the use job created subscription. Now inside components, make sure that you've pasted in the component created job list from the source code underneath the video. This will contain all of the UI for alert notification and the job list itself. It's just going to take one property jobs, that's going to be an array. And for each job, we need the ID and the title. So jumping back over to job created notification index.tsx, let's import here a bunch of packages. We need use effect and use state from React, import in job created subscription and use job created subscription from our generated types. So from queries.generated, then import the UI code for created job list from components. Let's create a type here, create a job, which is going to equal job created subscription and job created. So that will just equal ID and title. It just means we don't have to repeat any TypeScript code here. Now we can define a new component, job created notification. It takes no arguments. Let's just export this at the bottom. Then the first thing we need at the top is to actually use the subscription hook. So we say const data equals job created subscription. And this component will now re-render anytime new information becomes available from our subscription. So data will change every time a new job is created and we receive an event from the server. Let's create some state to keep track of all the different jobs, because data will only equal the most recently created job. If we do want to maintain a list, we need to do that manually. So we use state for that. At the moment, it's equal to an empty array, and that array will be equal to the created job type we've just defined here. Now let's define a use effect to push data to the new jobs state anytime data changes. So we'll define a use effect which changes when data changes. Then if data.jobCreated, let's push that created job onto the state, set new jobs, get the previous state, spread the previous state with the newly created job. Finally, we can just return created job list, passing the jobs across. Then the final thing to do is actually render job created notification somewhere. So let's jump into app.tsx. Then beneath auth provider, next to root provider, let's render job created notification. We'll import that, hit save, and now let's go ahead and run the server. npm run start. So on the left here, I've got Apollo server, and then on the right side here, I've got the application. We first need to log in as an admin because only admins can create jobs, and both of these windows will use the same cookie. So let's log in, admin@example.com, and then password 123. Now, when I hit create, you'll see this new UI appears telling me that a new job has been received, and I can create maybe one or two more jobs. Click on this and you see those jobs on the list here as well. So let's refresh this screen and then look at the network to see how WebSockets are working in this case. So we'll create a new job. We get the event received. Let's look for our WebSocket request. So we're looking specifically for this GraphQL request, which has two arrows pointing in either direction. This will contain all of the information that's being sent to our client. So if I hit create a bunch more times, you'll see more messages coming into this. GraphQL Network Inspector also has support for subscriptions. So if I just check this, you can see all the subscriptions coming in. If I keep it in create job, you can see all of the data appearing here as well. So a slightly nicer UI than the standard network tab. So there you have it. That is subscriptions in a nutshell. And just to refresh, the actual protocol that subscriptions work over is entirely up to us. It could be server sent events, subscriptions, even long or short polling could be supported as well. Subscriptions are just the methodology of sending data from a server to a client. WebSockets are actually a weird one because WebSockets support two-way communication, whereas subscriptions are always one-way communication only, always just from the server to the client. So maybe server-sent events are actually the better approach, or at least the better modern approach. Thanks for sticking around for this. I know that was a fairly long one, and I'll see you in the next video. Let's take a look at how we can effectively manage errors within our GraphQL application. On the front end here, I've got the create new job modal open. So I've logged in as an admin, click create job. And what we'll do is throw an error inside create job to see how that comes through on the front end. So let's just throw a standard error, throw new error. Let's just call it test, and then see what happens on the front end when we call create job. So at the moment, create job mutation is sent, and we get back an error with the message test. We also get the path, create job, and then some extension information. So at the moment, it just says internal server error, and then we get a full stack trace as well. Now, this is only coming back because we're in development mode. Once we're running in production, the stack trace will be omitted, so there's no risk of leaking any kind of internal information to the client. So as standard, this is pretty good as it is. We could send formatted error codes back and then respond on the front end accordingly. But we might not always want to send back every single error to the client. For example, if there was an internal server error that wasn't related to bad user input, we might want to log that to an external service, but not actually expose that to the client, and rather just send the message back like something went wrong. And we can do that in Apollo. So let's have a look at how we set that up. So inside server and index, we have the Apollo server being initialized here. And we can supply an argument called format error. So I say format error, we supply a function, and what we'll get here is the formatted error, so the error that Apollo itself has formatted that it would just send back to the client, and then the unformatted error as the second argument. Here we have complete control over the errors that are coming in, so we can format them, omit them, change them before we actually return data back to the client. For example, if we have a database error that I do not want to send back to the client, I could say if the formatted error dot message starts with database error, then return a message internal server error. Otherwise, return the formatted error. And that would mean if we run into any errors that have this particular format, we wouldn't expose that to the client, and instead we would return internal server error. So that's just a really basic way to show you how you can manipulate and omit certain errors on the back end. But that could be a fairly naive approach, like this isn't really scalable. What if we have a ton of different errors that we want to format? So let's, for example, look at throwing a Zod error. So we'll add some validation to the create job mutation now. And in this example, what we'll do is we'll update the validation to ensure that salary must be a value above 1. Because at the moment you can actually pass in a negative number into the salary field when creating a job. So at the top of resolvers for job, let's import Zod. And if you don't have Zod installed already, just do npmi Zod. Then we can create a schema for create job. Const create job schema equals z.object, and then we'll pass in the logic for each field. So title must be a string, location must be a string, description a string, type a string, remote is a boolean, salary is a number that must be above 1, and then company name must also again be a string. Now let's scroll down into the create job mutation so we can use this. So I'll remove this test error, and then let's just use this schema to validate the actual input. Create job schema.pass, pass in args.input. Now let's jump back over to the front end and then set this to a negative number, so minus 1000. I'll clear the network tab, and then we can now press create job again. And now the response we get back is the actual Zod error. So it's a stringified version of the message saying code too small, minimum is 1. And it also tells us it's for the field salary. The extension also just says internal server error. And then we have the stack trace here as well. Again, this would only come back in development, not on prod. But this error would be quite difficult to work with. So instead, let's use GraphQL's inbuilt error type, GraphQL error, which will allow us to send a much nicer error payload back to the client. So let's wrap this error in a try-catch block. And then when we catch this error, we can now transform it into a GraphQL error. So we'll say throw new GraphQL error, and that's going to come directly from the GraphQL package. So that's imported from GraphQL at the top here. Let's give it the message invalid user input. And then the most important thing is with GraphQL error, we can supply extensions. So this is a way to supply extra information to the client in a much neater way. The extension could have the code bad user input, and then we can supply the error itself from Zod. So let's save that and then give this another go. Create job. Now the error message looks a little bit nicer. So we've got the message invalid user input, we've got the extension bad user input, and then we've also included all of the errors from Zod. So this is already passed, and we could just use it directly on the front end to show any kind of error message to the client. But again, I think this could still be improved. So this would be quite tedious to repeat every time we want to throw a Zod error. So instead, why don't we just do it inside format error instead? So detect if an error comes from Zod. If so, transform the error into this format and then return it to the client. So again, let's remove the try-catch block and then just leave Zod to throw its own error. And now we'll detect Zod errors inside format error and then do the conversion here instead. So let's just remove this example code for now. Now, formatted error is not what we want to look at. We want to look at the original error here, which by default just has the data type unknown because GraphQL doesn't know which type of error it is at this point. So we need to help it out a bit. We say if error is instance of GraphQL error, then we can grab the original error. So we say if error dot original error, is instance of Zod error, importing from Zod. Then we can just return a nicely formatted error. So we'll return the message, invalid user input, and then the extensions again, passing the original error across. So original error in this case would be the Zod error. Otherwise at the bottom, let's just return the original formatted error. So I'll hit save on this, come back to the front end. Let's execute this query one more time. And again, inside error, we've got the message, invalid user input, and then the original error from Zod containing all of the validation issues. So by adding the code here, it means we've got a central place to format all errors that come in a particular format. Now, if you want to do any kind of omission or any kind of transformation of different error types, this is the place to do it. So now let's just switch over to the front end and see how we can display a nice message in the UI when this type of error occurs. So inside source and components, we've got this new component here, error, which will format the error that comes back from the server and then print it on screen in a nice new UI. You can copy this code from the course content just underneath this video so you don't have to write any of this UI yourself. But just pop this in a file called error.tsx inside components. Then we're going to look inside roots, admin, and then create job dialog. So here we're calling the create job mutation, and this returns the mutation itself and then a loading indicator. We can also grab the error directly from this hook. So when we execute this mutation here, create job, if an error is returned, it would become available on the next render within this variable. But at the moment, when we call create job, we get this large error coming up on screen because we haven't handled this promise rejection. So there's two ways you can handle errors. You could just get the response directly back from the promise. So I could say res here, and this would include the error as well. If, for example, you wanted to show a toast, here would actually be the best place to do it. You just await for the promise to resolve and then grab the error and then display a toast on screen. But we're just going to display the error UI somewhere down the bottom of the form. So let's just remove this and again wrap this in a try catch block. And then we'll just comment noop for now because we actually don't care if this promise fails. If it fails, we'll get the error coming back from this message here. So let's scroll down underneath dialog body and we'll say, if there's an error, let's render this new error component. And then we pass the error across. Let's hit save on that. Now with this in place, let's fill this format again. Test, 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 and then -1000. Hit create job. Now we get this nice UI appear on screen. Please fix the following 1 errors. Salary number must be greater than or equal to 1. Let's just add some padding to this to make it a little bit nicer. Margin top 4. And again, the network request just returns extensions, error, issues, which is an array, and that contains all of the Zod errors. Looking back at the source code for the error component, the whole error gets passed in. We pass it into this function format input errors. Here, we're just checking that the error is an instance of Apollo error. If it is, we grab the extensions error. So we've got all of the input errors. We then just cast that to Zod error. We map over all of the issues and then just concatenate the path with the message itself with the colon here. So that means we end up with salary colon number must be greater than or equal to 1. It's just about formatting your errors in a consistent way, using error codes, omitting errors that you don't want to expose, and then rendering those on screen with reusable components that know about the error format and then can predictably render the correct UI. And again, you might want to render different UI. You might want to show a toast, an alert, inline content like I've done here. It really is up to you, but just make sure that you stay consistent. Use format error so that you don't have to repeat code in each resolver and you'll be good to go. Now we've formatted our errors and we're getting those onto the client in a neat way, we need to look at how we can actually log and monitor unexpected errors and do performance monitoring as well. There's many tools available for this. For example, Apollo provides as part of its enterprise plan, Apollo OS, and you can log and send a lot of metrics to them. Otherwise, you can use a lot of third-party tools like Sentry, Datadog, New Relic, all of that kind of stuff. In this video, we're going to set up a free account on Sentry, install the Sentry SDK, and then send unexpected errors and performance information directly to Sentry. So let's jump ahead and start the setup. The first thing you want to do is install a package called Sentry Node. Let's say npmi @sentry/node. Then the next thing you want to do is head over to sentry.io, create a brand new account if you haven't got one already. So I've already got one set up here for Overstacked. And then when you set up an account, what they're going to do is give you a DNS URL, and we'll need this to initialize our Sentry SDK. So I'll head back over to the code, inside server, let's create a brand new file called instrument.ts. Let's say import star as Sentry from Sentry node. Then we call sentry.init. So we say dsn. Then you definitely want to set this as an environment variable, but for now I'm just going to paste mine in as a string. Then we want to set the traces sample rate to 1, and that's just a Sentry config to say send all of the errors to Sentry. Then we want to configure one integration, and that comes from sentry.graphql integration. With this configured, and once it's imported into our index file, Sentry will automatically track all of the performance metrics for our GraphQL server. But there's one argument that we may want to pass the GraphQL integrations, and that is ignore resolve spans false. So this is set to true by default. But if it's true, Sentry won't track the performance metrics for individual nested resolvers. If you do want to find out where your resolvers are spending the most time, for example, let's look at the job schema. So we have job, we have isApplied, that's going to be a nested resolver defined here. If this particular nested resolver was running really slowly and we want to debug where the time is spent, then you want to make sure this is set to false. If you omit it or it's set to true, you're just going to get an overall time for the root resolver. Maybe omit it by default, but then in production, if you're finding that a particular resolver is slow, turn this off, then deploy the application again, and then you can start to inspect at which point within the graph most time is being spent. This will all make sense more when I show you the Sentry dashboard in a second. But let's jump back over to index, and then right at the top of the file, before we import literally anything, let's import instrument. And this means that Sentry is going to initialize before anything else is initialized and catch any errors to do with startup or within our server itself. Because we're using Express as well, Sentry can automatically track a lot of errors related to Express. So at the top here, let's just import Sentry again. Import star as Sentry from Sentry node. And then down at the bottom, underneath all of our middleware, now we can say sentry.setup Express error handler, and then just pass in the app here as well. And with that in place, it just means that Sentry will now automatically track a bunch of stuff related to Express as well. So with this in place, we can then boot up the server again. Now we can click around, we see a bunch of queries being executed, search jobs, the profile query, the admin query. And then inside Sentry, if we look under the performance tab, we can see all of these queries being executed. So we've got query for me, admin, a bunch of other stuff, profile, search jobs. So this is all the stuff that's automatically now being tracked by Sentry. So if I look inside search jobs and then click into spans and then default, then let's just check the latest event. You can see for every single job that was returned, it tells us exactly how much time was spent in every single nested resolver. So this is what I meant when I said set ignore resolve spans to false. If this was true, we wouldn't get any of this extra data, we'd just get a single time, so say like 20 milliseconds. Now you might not want all of this information being sent to Sentry. It could be, depending on the plan you're on, you could overload Sentry with too much data, so maybe turn it off by default and then only enable this feature if you actually want to debug a particular resolver. But it is a really nice feature, so you can really get into the weeds of where your server is spending most time. Now this is great because we're already tracking performance for both Express and our GraphQL resolvers, but no errors at all will actually be coming into Sentry at this point. And the reason is, when you throw an error with GraphQL, let's look inside search jobs, for example, and then just throw a random error here. Throw a new error, test, we'll come back to the app, I'll go to job search. Now we've got this error coming back. You'll notice, even though I'm throwing an error here, the response from GraphQL server is still status 200. So that's typical of the GraphQL spec, to always return status 200 and then just return the error in the response payload. But because this is status 200, Sentry doesn't see it as an error and doesn't automatically send anything to Sentry. So we need to supply our own plugin to be able to track errors and then send them to Sentry manually ourselves. Now you might think that you could do this inside format error, but that's not really the purpose of this function. This is just purely to format errors before you send them back to the client. This is also only called once the resolver has fully executed, right before the error is returned to the client. And that's probably not the best time to be sending errors to Sentry. We want to send an error to Sentry the moment it occurs, prior to any other further code being executed. And to do that, we can just define a new plugin that has very fine-grained control about when errors are being sent. Inside server, let's create a new folder here called plugins, and then we'll create a new file called Sentry plugin ts. And here we want a bunch of imports again. We want Apollo server plugin coming from the Apollo server package, GraphQL error, import Sentry again, and then also import context. We'll define a new plugin called Sentry plugin. This will equal the type Apollo server plugin, and then passing in the context into this generic. Then we return an object and then supply an async function called request did start. So anytime any request is executed, this is going to get called. From here, we can return another object, and this can include a bunch of stuff. So with all of these callbacks, we can hook into any section of the Apollo GraphQL lifecycle and then send any kind of information to any service we like. In this case, we're just going to deal with errors. So again, I'll pass another async function, did encounter errors. This is going to give us the errors themselves, the operation name, and then the full request. We can then loop over all of the errors and then decide which errors we want to send onto Sentry. So we say for const error of errors. Then let's grab the original error from this error. Const original error equals error.original error, because again, GraphQL will just turn everything into a GraphQL error. So we actually want to get the underlying error that was directly thrown within the resolver. Then we say if the original error is an instance of GraphQL error, then let's just do nothing for now. And I'll explain why we do this in just a second. But for any other type of error, let's just send that onto Sentry. So we say Sentry with scope and then provide a callback for that. And what this will do is allow us to attach a load of information to a Sentry exception before we finally send it onto them. So let's just set all of our scope information. We say scope, set tag, and then the operation name, passing across the operation name. So this would be the actual query or mutation itself that we've executed. Set extra, query, so the entire query payload. Set extra again, variables, so all of the query variables. Then set level to error. And then finally, Sentry.capture exception, passing the original error code across. Hit save on that. Then let's just export this function, export default Sentry plugin. Then back inside index, we can now use this plugin. Inside Apollo server, we say plugins, provide an array. And inside here, we include our new Sentry plugin, imported from plugins, Sentry plugin. Now with that in place, inside resolvers, we're throwing this error here, throw a new error test. If I come back to our application and refresh this screen, inside issues, I should now have this error coming in. So here we have this error that was thrown 6 seconds ago, just called test, and it includes a bunch of information that we attached. So here we've got the entire body, the operation, the query itself, all of the variables that were being sent, and even though it's just a post to the GraphQL endpoint, we can still see that it is directly for the search jobs query. Now this is only making it to Sentry because we threw a regular error. If, for example, I threw a GraphQL error, and then let's call that another error here. If I come back to the job board, refresh, we get the error coming back as another error. If I look inside issues, we don't see this second error coming into Sentry. And that's because inside the plugin, we've said if the original error is of type of GraphQL error, then let's return. Because if the error that we run into is due to, say, bad user input, those are expected errors. So we don't want to flood Sentry with a bunch of errors that we expected. We only want to know about the errors we didn't expect. So inside this for loop, you can choose to omit certain error types. Maybe you've defined a custom error called user error, or in our case, just GraphQL error. But it just allows us to choose what we do and do not send to Sentry to prevent us from overloading the system with errors that we don't actually care about. So that is an example of automatically sending performance data and errors to Sentry. Of course, you can integrate with a bunch of third-party tools like New Relic, Datadog, anything like that. But regardless of which provider you use, the implementation is mostly going to be the same. You're going to define a plugin. So we could have Sentry plugin, we could have New Relic plugin here. We'll call request did start. We'll grab the errors with did encounter errors, and then we'll choose which errors we want to ignore and then which errors we want to pass on to that third-party system. Sentry is also pretty nice because it automatically tracks all of these spans or telemetrics that it calls them literally through the Sentry GraphQL integration. If you're using a different provider, you might have to extend your plugin to manually send across different types of logs. So as we specified before, there's many different things you can hook into here. Did resolve operation, execution did start, will send a response. So these don't always just hook into negative things, they can hook into positive results as well. So if you just want to track things like performance, these plugins are still the place you would do it. But that is the basics of how you log and monitor a production GraphQL application. Up until now, whilst building the GraphQL application, everything has been built as a monolithic application. And we've had all of our entities, user, job, and company for the most part, and they've all existed in a single application. Inside our server, we have entities, company, job, user, and those were all combined together as a single schema within the context of a single application. This works wonderfully and can scale massively. In fact, I've worked on huge projects with hundreds of entities that have just operated as a monolith, and when you separate out your entities in this kind of folder structure, you can scale to a pretty huge level. But there will be some point or some reason in the future where you don't want to build a monolith. You might want to move to a microservice architecture, and that is completely possible to do with GraphQL. Since we're using Apollo, they already provide a bunch of tools to separate our entities into separate microservices, which can be combined through something called Apollo Gateway. Each of the smaller entities in this context are called subgraphs. So if we look at the entities so far, we have user, job, and company. And this currently all exists within the monolith, so this box here. The client sends requests in, and everything is handled within a single application. We can change this architecture. So what we're going to do in the next video is look at a simple example just using user and job, where we have the client sending requests to a server called our gateway, and then job and user will be entirely separate services that are deployed separately, exist entirely separately, but can communicate with each other via gateway. So the client sends requests in to a server gateway. It will then collect all the information it needs from the separate microservices before finally returning a complete payload to client. If we look at the Apollo server for an example search jobs query, we can request information about the jobs themselves, so the ID and title, and then also grab the user, so the created by user of a particular job. In this architecture, user is coming from a user microservice and search jobs is coming from a jobs microservice. So when I run this query, we get all of the data back, but it's come from completely separate places. So you can see how this would be a massively scalable architecture, especially for enterprise. In the next video, we'll go through all of the code for this example microservice architecture and start to see how all of the relationships work between the different entities. Inside our monolith, inside server, we have all of these entities, company and job. And in this video, we're going to architect this application through microservices instead. So what we have here is three entirely separate applications: the gateway, the job graph, and the user graph. Job graph and user graph are called subgraphs in this context, and they'll control data access just for the job entity, and then data access just for the user entity. Gateway is the application that sits right at the front that the user actually sends requests to, and then it will distribute requests out to all of our subgraphs, request all of the information it needs before it finally returns a complete payload to the client. And when I say these are separate applications, I mean literally they have their own package JSON, their own node modules. They can be deployed separately, updated separately. They can even be written in separate languages. It doesn't have to be TypeScript or JavaScript in this context. So let's have a look at the code for each one. Inside Gateway, we import Apollo Gateway and introspect and compose from the package Apollo Gateway. You can install this with npmi apollo/gateway. We then just need the standard Apollo server package, apollo/server, and just because this is a small example, we're using the start standalone server coming from the Apollo server package as well, although you could launch your server with Express or anything else like that. When we work in this microservice architecture, Gateway doesn't define any types itself. It just calls out to the separate subgraphs. So rather than passing a schema into Apollo Gateway, we pass in supergraph SDL and then a new instance of introspect and compose. Inside that, one object, subgraphs. This names all of the different subgraphs and then also tells Apollo which URL that subgraph is running on. All of these subgraphs will be running on separate URLs. In this case, it's just localhost, but in reality, maybe you've deployed that to AWS or any other sort of cloud architecture. So in this case, we just have jobs and users. Then we initialize Apollo server, passing in our new gateway. With that server initialized, we can just start it like we would any other server. So in this case, we just pass it to start standalone server, listen on port 4000, and then we're good to go. So the setup for the gateway itself is very simple. In this case, all of the subgraphs are unauthenticated, but you could pass in extra information like the introspection headers, which you definitely want in a production environment. Now let's look at the first subgraph, so job subgraph in this case. We look inside index. Again, we've imported Apollo server, start standalone server, and then from the Apollo subgraph package, build subgraph schema. Then we just need GraphQL tag. We have some mock data being returned here, just a regular async function returning an array containing a single job. We've got the job ID, the title, and the created by user ID. So this is the first relationship that we've defined so far. Now the schema is going to look a little bit different than what we're used to. We define our type job, and then we have this new directive here, key. In Apollo Gateway, key helps us define the primary key, where we can think of it sort of like a primary key for a particular type. This key needs to reference a field that can be used to uniquely reference a single type across all of the other subgraphs. In most cases, you probably just want to pick ID. So we've done that. Fields ID references the ID on job. Then we have title, and then we have created by, which references a user. Now, we've defined user type inside our job subgraph, but all we do is define the ID and then state that this is an external field. We also use the same key directive here just to say that we will uniquely identify user by its ID. The only query we have here is search jobs, which just returns an array of jobs. In our resolvers, we have search jobs, just returning our dummy data via fetch jobs. And then in a very similar way as we did in our microservice architecture, we still define the direct relationships to our job type. In the case of job, we have the relationship created by. This will receive a job, and all we need to do is return an object with the type name user and then the user's unique key. So in this case, the ID. That value is coming from job created by user ID, which is defined inside our dummy data here with the value user1. So it's going to be important that the job subgraph has some reference to user, but it can be as minimal as just an ID. With that in place, we pass the schema into Apollo server via build subgraph schema, passing in the type defs and resolvers, and then again, just start the server as normal. Inside the user subgraph, we have a very similar setup. So the same imports as we did in the job graph, and then some dummy data being returned, fetch user by ID. We return an ID and an email, and in this case, we're passing in the ID. So whatever ID we pass in will just be returned for this dummy user. We define the query me to get the current user. And then we define the user type, again, passing the key directive with the field's ID. We return the ID, the email, and in this case, another relationship, applied jobs, which will return an array of jobs. We then again, on the user subgraph, define the type job. And again, all we provide is the ID and then the directive to say that's an external field. Inside the me query, we just fetch the dummy user. And then inside user, we've defined our relationship here, applied jobs. And in this case, again, we're just returning an array of dummy jobs. But again, all we provide is the type name and then the job ID. Again, we then initialize our server in exactly the same way as before. So if we boot up all of our servers separately, npm run start on job graph, npm run start on user graph, and then npm run start again on the gateway. With that in place, I could run a query here, which returns all of the jobs. So our dummy job with the ID job1, software engineer, and then also created by, which in this case is going to return a user. So let's see how this is working under the hood. Inside the job graph, we have the search jobs query, which we've executed here at the top level. This will return all of the jobs. So the dummy data here, ID job1 and title software engineer. The only relational data we have here is created by user ID, which will just have the user ID user1. Since we're accessing the relational field created by, we have that defined here, which will just return the object with type name user and then the job.created by user ID, so user1 in this case. That information will get sent back to gateway, which will then send it on to the user graph. And then inside user, resolve reference would be called with that data from job graph. So we'd get a user with just the ID on, and that ID would be equal to user1. So if I look inside user graph again, and let's add a log here, console.log user, then just restart the user graph. If we then execute this query again, you'll see that we get a log here. So user, type name user, and then ID user1. That is the exact value coming from the created by nested resolver on the job graph. We can then use that information to grab all of the other details about a particular user. So all we have is a user ID, but then by calling fetch user by ID, we can also grab the email as well. Again, that information is passed back to gateway, and then we result in a query which has the data from all of the different subgraphs resolved. So you can see how agile this is. We could have hundreds of different entities controlled by completely separate subgraphs that can be deployed separately, worked on by separate teams, and then through simple relationships defined in each subgraph, we can connect all of those pieces together. The way of thinking about this is very similar to how we would also do it with the monoliths. Inside our monoliths, we also only care about the direct relationships. So user would reference job, but user would never reference anything about the job's company. All of that would be referenced inside the job entity itself. And you can think in the same way when we do the microservices as well. But that is just a quick rundown of how microservices work. There are plenty of third-party tools out there to provide microservices. It doesn't have to just be Apollo, but Apollo is a great and very popular tool to do this with. All the caching mechanisms that we've looked at so far have purely been client-side. We haven't at all looked at server-side caching. So in this video, let's do a deep dive of how we can do server-side caching with GraphQL. So the typical approach that you do caching with any server, say a standard REST server for example, would be that you have a client. It would send a request that goes via a CDN, that goes on to the underlying server. The server responds with some sort of cache header, say max age 60, that gets passed back onto the client. And then next time, client B sends a request, the CDN would have cached that request due to the cache headers coming from the underlying server. So client B's request doesn't go to the GraphQL server in this case at all. This model is still completely possible with GraphQL, but it won't work out of the box. And that is because GraphQL queries by default use POST requests, and POST requests are not cacheable by most CDNs. So what we need to do is switch our GraphQL server over to using GET requests and then look at some of the known limitations around that as well. By the end of this video, we'll be able to send queries to our GraphQL server that respond with cache control headers like this one here, max age 30 and public. So let's just jump over to the code and start implementing this feature. Now, since we're using Apollo, they already support out of the box, or almost out of the box at least, some directives for cache control. So against any field, say for example search jobs here, we can supply a directive cache control and then give it a value like max age of 60. But if we were to add this to our server, by default it will not work because we need to do a little bit of upfront configuration so Apollo knows what to do with this cache control directive. But once it is configured, the server will respond with the correct cache control headers. So inside server and index, the first thing we want to do is import the cache control plugin, and that's called Apollo Server Plugin Cache Control. So inside plugins here, we can implement this new plugin. So just paste it in and then give it a default max age, let's say 60 seconds. This means that every query in our GraphQL server will now have a default max age of 60 seconds coming back. This is a pretty good setup if you do want to just cache everything, otherwise you can set the default max age to 0. But let's stick to 60 for now. Then the other thing we need to do is just tell Apollo what these cache control directives actually look like. So following the same pattern as we did with our other directives, let's add a new folder here called Apollo. In here, we'll add a schema.graphql. And then from the Apollo docs, they actually give us these cache control directives. And it says here, to use the cache control directive, you must add the following definitions to your server schema. So we can just copy this, paste it in here, and here's the URL, apollographql.com/docs/apollo server/performance/caching. We paste that in, and then let's follow the same format as we did for our other folder. We'll give this an index.ts, import typedefs from schema.graphql, and then export those typedefs. Then inside schema, we can now import the new directives. So import typedefs, Apollo directive typedefs, and then supply them into the typedefs array under make executable schema. With that in place, we can go to an entity like job, schema, then under search jobs, add our cache control header, give this one a max age of 30, for example. Then we can just run our server, npm run start. Then if we look over at the application under search jobs, headers, we can see we have the cache control header with the max age of 30, which we defined in the directive here. Now this is pretty good for localhost, but it won't work over a CDN because this query is still using a POST request. So if we look inside the network tab at all of our GraphQL requests, you can see they're using the request method POST. So we need to configure the server to be able to use GET requests instead. And we can do that with a really simple config change on the client.ts. We have the create HTTP link, and here we can add the argument use get for queries and then set that to true. If I save that and then rerun this request again, you'll notice that all of these queries look a bit different now. The query itself has been added as a query string, and then the request method is now get. So rather than just sending a request just to our server/GraphQL, we now have the query string appended. Now Apollo will already be able to pick this up, parse it, and respond with the correct response. Now again, this is pretty good, but you still might run into errors because these GraphQL queries can get pretty huge. Just look at this request for search jobs. So if we look at the payload that's being sent, the entire query plus any of the variables are being stored inside the query string here. Now there's a recommended limit of around 2,000 characters for these query strings. If you go any larger than that, then certain servers or reverse proxies are going to reject your URL and then they just won't work. So depending on the system you're using or the CDN you're using, you're going to quickly run into limits with this approach. But Apollo are already aware of this issue, and so they've already supplied a solution for us, and that's called persisted queries. Persisted queries work by converting our large query to an SHA-256 hash. The hash and the query itself is stored on the server, so then the next time we make a request, all we have to send up is the hash. The server can then find the related query and then execute it and then return a result. This means we can send GET requests with huge queries without running into URL size limits. So there's two things we need to do to configure this. One change on the client and then another change on the server. So since we're already inside client.ts, let's import a new package from Apollo. This is called create persisted query link from Apollo client link persisted queries, and you'll already have this installed. We then need one more package, SHA-256 from crypto hash, and then we can just install this as well, npm crypto hash. Then below HTTP link, we'll define a new link here, const persisted HTTP link, which equals create persisted query link. We pass into it the SHA-256, then use get for hashed queries, which means we don't need this option here anymore. So I'll just comment that out for a sec. Then we say dot concat and then pass in the HTTP link. Then finally at split link down the bottom here, rather than having the second option be HTTP link, we just pass in the persisted HTTP link instead. Hit save on that, then head back over to server index.ts, and then inside the server config for Apollo server, we just need to pass one option, persisted queries, and then give it a default time to live, and then say 60. And this is because persisted queries themselves are stored on the server, so the hash and then the query. So this is a time to live for how long that query will live in memory. This has got nothing to do with caching headers, it's purely about the persisted query itself. If we run this server one more time, now previously where we had this huge request for search jobs, we now have a much smaller request. So we see that we're still sending a GET request to localhost 4000/GraphQL. The operation name is search jobs. We still pass up the variables because they can't be cached, but then the query itself is cached as this SHA hash. So if we look at the payload here, we've got the operation name, the variables, and then this extensions which contains the persisted query. The server still responds with the JSON payload. So I've just logged in as a user and now I'm looking at the profile section of the application. You can see in the GraphQL Network Inspector, we actually show these persisted queries in a much neater way. So we show a letter P for persisted queries, and then I can look inside of this, inside the request, I see the persisted query just being sent with this SHA-256 hash, and then the response coming back here as well. Now the response headers for both profile and me are going to be set to 60 because this was the default max age that we set for our server. But certain requests, like me for example, you would not want to cache, because this is returning the currently authenticated user. So if this got cached against a CDN, the next time another authenticated user requested me, they'd actually get access to a different user, which is really bad. So in that case, there's two options. You can either, by default on the server, set the default max age to 0, or still keep it as something like 60, but explicitly set all of these sensitive queries to max age 0. So I'll take cache control here, we'll go into user, schema, and then for the me query, just set the cache control to 0, restart the server. Now you see both me and profile have a cache control of no store. So these camel cased queries are actually the local query name, but they're actually both sending the me query onto the server. So they both have a cache control of no store. You don't have to just set cache control on fields here as well. You can actually just set it anywhere. So I could just set it on, let's say, the user's ID or the user's email. And this is a little bit misleading because it seems like Apollo can cache individual fields, but what it's actually doing is it's computing the entire query. If it comes across multiple cache controls or a single cache control, it will use the lowest number cache control for that entire response. So if, for example, we have on the me query a cache control of 30, and then on ID we have a cache control of 0, if I rerun this server, it just means that me will still have a cache control of no store because ID was the cache control that it found with the smallest max age. So don't let this fool you into thinking that you can cache individual fields. It's still actually just for the entire request. If you do want to cache individual fields, that is possible, but you need to use application level caching. So with a system like Memcached or Redis, and then you'd have to define your own directives and plugin. So we could have something here like cache and then pass a value like TTL 60. And then our directive could pick this up, send the request onto Redis or cache data into Redis, and then send the results back to the client. But for the typical approach of using the CDN, it's these cache control headers that you want to use. Now you'll notice as well, when you restart the server, the first request that gets sent will fail, and then we'll send a regular non-persisted request. So if I look inside the network tab here, we can see that this was sent as a GET request. The response is persisted query not found. And then we send that request on again, but this time it's just a standard POST request. Because when the server starts, none of these persisted queries are stored in memory. So the client will send the request, it will fail. Apollo client will then automatically resend a regular POST request, which will then get stored on the server in memory. And then next time we execute that request, we will now have the persisted query to send. And that's just due to the fact that we're storing the persisted queries in memory. On the server side, inside persisted queries, we could provide a separate cache. This just needs to be a key value store, and it doesn't have to be in memory. Again, you could use Redis or Memcached or anything else for this. So when your server restarts, or if you have multiple servers launched, they can share the cache between each instance. But with all of that in place, if you then use a CDN, it should automatically be able to pick up these cache headers because now they're just standard cache headers. And then you'll have an effective caching solution between multiple clients. If you've managed to make it this far, then congratulations. You now have the skills needed to build production-ready GraphQL applications in industry, at scale, at any company. If you want to see more from me, then check out some details in the video description, and it'd be super helpful if you do subscribe. I'll see you next time.